The planet Saturn has more than 80 moons spinning around it, but one of them is completely different from anything we know. It's called Titan, and it's a huge world, even bigger than the planet Mercury. For a long time, we thought Earth was the only place with liquids on its surface, but Titan changed everything. It has lakes, rivers, and even gigantic seas. The shocking part? It's not water. It's liquid methane, the same type of gas we use in stoves, but so cold it turns into a liquid. The orange and dense atmosphere hides mountains of ice as hard as rock. Prepare to fall asleep while listening to this video about this incredible journey. How can a place so cold and strange look so much like Earth? Subscribe to the channel, leave your like, and comment what part of the world you are watching from. Get comfortable and relax. Let's begin. Imagine a world where rivers flow not with water, but with methane, and the sky is a perpetual orange haze. This is Titan, Saturn's largest moon, and it is completely redefining what we consider a world to be. When we picture moons, we often think of small, barren rocks, silently orbiting their planets. But Titan shatters that image entirely. It is not just another moon. It is a complex and dynamic place that rivals many planets in both size and activity. In fact, Titan is larger than the planet Mercury, and if it were orbiting the Sun independently, we would likely classify it as a planet itself. However, it remains bound to Saturn, yet it possesses features that blur the lines between moon and planet. One of the most astounding attributes is its atmosphere. Titan boasts a dense, thick atmosphere that is unique among all the moons in our solar system. This atmosphere is primarily composed of nitrogen, much like Earth's, but it is enriched with methane and other hydrocarbons, creating a thick orange haze that obscures the surface from view. The atmospheric pressure at the surface is about 50% higher than on Earth, meaning that while you would not need a pressurized suit to withstand the pressure, you would require protection from the extreme cold and a respirator because the air is not breathable. This haze is the result of complex chemical reactions driven by sunlight, which break down methane and nitrogen, leading to the formation of various organic compounds that give Titan its distinctive color. Beneath this haze lies a landscape that is both familiar and utterly alien. Vast dunes made of organic particles, similar to sand dunes on Earth but composed of hydrocarbons, stretch across the equatorial regions. There are plains that may be covered in water ice, and mountains and hills also made of water ice, which behaves like rock at the frigid temperatures. Most intriguingly, Titan has rivers, lakes, and even seas of liquid methane and ethane. These are not small features. There are seas larger than the Great Lakes on Earth, with the largest, the Kraken Mare, being bigger than the Caspian Sea. This indicates that Titan has an active hydrological cycle, but with methane playing the role that water does on Earth, methane evaporates, forms clouds, rains down, and flows back into the seas, sculpting the surface over time by creating channels, shorelines, and deltas. The presence of these liquid bodies means that Titan experiences weather patterns and seasons. Since Saturn takes about 29 Earth years to orbit the Sun, each season on Titan lasts roughly 7.5 years. During the northern summer, for instance, increased sunlight leads to more evaporation and rainfall, particularly filling the lakes and seas in the polar regions. This active surface system raises the question, how does a moon support such dynamic processes? The answer lies in Titan's relationship with Saturn. Titan is subject to intense tidal forces from Saturn's gravity. As Titan orbits, the gravitational pull stretches and squeezes it, generating internal heat through friction. This heat helps to maintain Titan's interior warmth, possibly sustaining a subsurface ocean of liquid water mixed with ammonia, which acts as an antifreeze. The existence of this ocean is inferred from measurements of Titan's gravity field and how it deforms under Saturn's influence. This internal heat might also drive geological activity such as cryovolcanism, where volcanoes erupt water, ammonia, or other volatiles, instead of molten rock. This means that Titan is geologically active, with processes that continuously reshape its surface. When we compare Titan to other celestial bodies, its uniqueness becomes even more apparent. Scientists often draw parallels between Titan and early Earth because both have nitrogen-rich atmospheres and complex organic chemistry. On early Earth, similar conditions eventually led to the emergence of life. On Titan, the chemistry occurs at much colder temperatures, around -179 degrees Celsius, but it still produces complex molecules like amino acids and nucleobases, which are the building blocks of life. This does not mean life exists on Titan, but it demonstrates that the processes capable of leading to life are not exclusive to Earth. Additionally, Titan's atmosphere fosters the formation of tholins, complex organic polymers that contribute to the surface's reddish-brown hue. Another point of comparison is Jupiter's moon Ganymede, which is actually larger than Titan but lacks a substantial atmosphere and surface liquids. Titan's thick atmosphere and liquid features make it more Earth-like in terms of having an active surface system. The methane in Titan's atmosphere is continuously destroyed by solar radiation over geological timescales, so there must be a source replenishing it. This source could be cryovolcanism releasing methane from the interior or slow seepage from subsurface reservoirs. Understanding this methane cycle is crucial for comprehending Titan's long-term climate stability. The study of Titan is vital because it challenges our conventional definitions of what makes a world habitable or dynamic. Habitability is not solely about being within a star's habitable zone. It is about having the right conditions for chemistry, liquid solvents, and energy sources. Titan has liquid methane on the surface, possibly liquid water underneath, and abundant organic materials, thereby expanding the range of environments where we might find prebiotic chemistry or even life. Moreover, Titan's active processes, including weather, geology, and tidal interactions, show that moons can be as dynamic as planets. This forces us to reconsider our categories and definitions of celestial bodies. In the broader context of the solar system, Titan serves as a powerful reminder that worlds come in many forms, and our understanding must be flexible enough to accommodate this diversity. Missions like Cassini-Huygens have already revolutionized our knowledge. The Huygens probe landed on Titan in 2005, sending back images and data from the surface, while the Cassini orbiter provided detailed maps through radar and infrared observations. Future missions, such as Dragonfly, a drone designed to fly through Titan's atmosphere, will further explore this enigmatic moon. Each new discovery reinforces the idea that Titan is not merely a moon, but a world in its own right, challenging our perceptions and enriching our comprehension of the cosmos. So, when you gaze at the night sky, remember Titan as a place that defies simple classification, teaching us about the incredible variety and potential of worlds beyond our own. But how did we go from seeing Titan as just a faint point of light to understanding it as this complex, Earth-like world? The story of its discovery and our evolving observation is a fascinating journey of human curiosity and technological advancement. It all began back in the year 1655, when the Dutch astronomer Christian Huygens, using a telescope he built with his brother, first identified Titan orbiting Saturn. This was a monumental discovery because it was the first moon found around Saturn, and it opened our eyes to the fact that other planets could have their own companions. For centuries after that, Titan remained little more than a speck in telescopes, a mysterious dot whose true nature was completely hidden from us. Astronomers could track its orbit, but that was about the extent of their knowledge. The big shift started in the early 20th century, when new techniques in spectroscopy allowed scientists to analyse the light coming from Titan. They noticed something extraordinary. The light signatures suggested that Titan was surrounded by a substantial atmosphere. This was utterly unique. No other moon was known to have such a thing. The idea that a moon could hold onto a dense atmosphere captured the imagination of the scientific community and set the stage for the space age. The first spacecraft to visit the Saturnian system was Pioneer 11 in the late 1970s, but its observations were brief and it did not get a very close look. The real game changers were the Voyager missions. Voyager 1, in particular, made a close flyby in 1980, and its images and data transformed Titan from a fuzzy orange ball into a world shrouded in an impenetrable haze. The Voyagers confirmed the thick atmosphere and provided the first concrete data about its composition, showing it was mostly nitrogen with methane and other hydrocarbons. However, the haze prevented any clear view of the surface, leaving a major mystery unsolved. For decades, scientists puzzled over what might lie beneath that orange veil. Was the surface solid, liquid, or something else entirely? This burning question drove the planning for a dedicated mission, which culminated in the Cassini-Huygens project, a collaboration between NASA and the European Space Agency. The Cassini orbiter, launched in 1997, arrived at Saturn in 2004 and began an unprecedented long-term study of the planet and its moons. Cassini carried a probe named Huygens, destined specifically for Titan. The Huygens probe separated from Cassini and descended through Titan's atmosphere on January 14, 2005, parachuting down to the surface. This was a historic moment. For the first time, humanity was landing a probe on a world in the outer solar system. During its descent, Huygens transmitted data and images, revealing a landscape with hills, channels, and what looked like a shoreline. It even sent back sounds of wind during the descent. When it landed, it survived for a short time on the surface, sending pictures showing a plain littered with rounded ice pebbles, evidence of fluid erosion. Meanwhile, the Cassini orbiter continued to make over 100 flybys of Titan, using its radar and infrared instruments to pierce through the haze and map the surface in incredible detail. Cassini's radar revealed vast dunes, large lakes and seas, and even possible cryovolcanoes. It confirmed that the lakes were filled with liquid methane and ethane, and it discovered that Titan has a hydrological cycle similar to Earth's, but with methane instead of water. The mission also gathered evidence for a subsurface ocean of liquid water, adding another layer of complexity to this already intriguing moon. The data from Cassini-Huygens is so vast that scientists are still analysing it years after the mission ended. But the story of observing Titan did not stop with Cassini. Today, powerful telescopes like the James Webb Space Telescope are now turned towards Titan, observing it in new wavelengths and complementing the in situ data from the missions. These observatories help monitor changes in Titan's atmosphere and surface over time, such as seasonal variations and weather patterns. The evolution from a simple point of light to a mapped world with known geology and climate shows how far we have come. Each step in this journey built upon the previous one. Huygens' discovery gave us the object. Spectroscopy hinted at its atmosphere. Voyager confirmed the haze, and Cassini-Huygens unveiled the surface. This progressive unveiling was made possible by international cooperation and leaps in technology. It is a testament to human ingenuity that we can send spacecraft across billions of miles to explore another world. The journey of observing Titan is also a story of patience, as missions take years to plan and execute, and data analysis can take even longer. Yet, each new piece of information has radically changed our perception. We now see Titan not as a distant, enigmatic moon, but as a dynamic world with processes that are both alien and familiar. This evolving understanding continues to inspire new missions, like the planned Dragonfly drone, which will further explore Titan's surface in the coming decades. The discovery and observation of Titan remind us that exploration is an iterative process, where each generation builds on the knowledge of the past to uncover new mysteries. From a single observation in the 17th century to the sophisticated probes of the 21st, our quest to understand Titan has been a relentless pursuit, driven by the desire to know what lies beyond our own world. And as we continue to look, both with telescopes from Earth and with spacecraft, we are sure to learn even more, perhaps answering the biggest question of all: could life exist in such a strange and cold environment? The tools we use may change, but the fundamental curiosity that drives us remains the same, pushing the boundaries of what is possible in our exploration of the solar system. Now, having mapped its surface and understood its history of observation, we must dive into the element that makes Titan truly stand out: its incredible atmosphere. This is not a thin, wispy layer like on some other moons. Titan's atmosphere is a dense, active, and complex system that defines the entire world beneath it. In fact, it is about 50% denser than Earth's atmosphere at the surface level, which is a staggering fact when you consider that Titan is only a moon. If you were standing on Titan, the atmospheric pressure would feel similar to what you experience at the bottom of a swimming pool on Earth. This high pressure has profound implications. For one, it means that you would not need a pressurized spacesuit to withstand the pressure itself. Your body would not explode or suffer from the bends in the same way it would in the vacuum of space. However, you would absolutely need a very strong thermal suit because the surface temperature is around minus 179 degrees Celsius, cold enough to instantly freeze any exposed flesh. You would also need a respirator because the air is not breathable. It is mostly nitrogen, like Earth's, but lacks oxygen and is filled with other gases that are toxic to humans. The composition of this atmosphere is what sets it apart. About 95% of it is nitrogen, with most of the rest being methane, along with trace amounts of other hydrocarbons like ethane and propane. This methane is the key player in Titan's atmospheric drama. Sunlight, particularly ultraviolet radiation from the sun, strikes the upper atmosphere and breaks apart the methane and nitrogen molecules. This breakdown triggers a cascade of chemical reactions, creating more complex organic molecules. These molecules include things like ethylene, acetylene, DOT, and hydrogen cyanide, which are the building blocks for even larger compounds. These complex hydrocarbons then coalesce into tiny particles that form a thick, orange haze that envelops the entire moon. This haze is so effective at scattering light that it gives Titan its characteristic orange-brown colour and prevents direct observation of the surface in visible light from space. This haze is not static. It is a dynamic part of the atmosphere that undergoes constant change. The particles in the haze eventually grow large enough and sink lower into the atmosphere, where they act as condensation nuclei for methane clouds. This leads to another amazing aspect of Titan's atmosphere: its weather. Methane on Titan plays the role that water does on Earth. It evaporates from the surface, forms clouds in the sky, and then falls back down as rain. This methane rain carves river channels and feeds the lakes and seas we see, particularly near the poles. So you have a full hydrological cycle, but with methane as the working fluid instead of water. The chemistry happening in the atmosphere is often called prebiotic chemistry because it produces many of the same organic molecules that are thought to have been important for the origin of life on Earth. On Earth, these reactions happened in warm oceans, but on Titan, they are happening in the frigid upper atmosphere and on the cold surface. This makes Titan a natural laboratory for studying the chemical steps that might lead to life under conditions that are completely different from early Earth. The organic snow that falls from the haze accumulates on the surface, potentially building up layers of organic material hundreds of meters thick over geological time. Imagine vast dunes not made of sand, but of hydrocarbon grains, or plains covered in a tar-like substance made from these complex organics. This material could be incredibly important for understanding the limits of organic chemistry in the universe. The constant production and deposition of these molecules mean that Titan's surface is rich in carbon-based compounds, which are the essential ingredients for life as we know it. However, the extreme cold poses a challenge for life. Chemical reactions happen much more slowly at such low temperatures. Yet, the presence of liquid methane and ethane on the surface, and possibly a subsurface ocean of liquid water, provides solvents where different chemistry could occur. The atmosphere also plays a role in Titan's climate and heat distribution. Despite being so far from the sun, Titan has a greenhouse effect caused by methane and other gases in its atmosphere. This effect helps to trap what little heat it receives, preventing temperatures from dropping even lower. However, there is also an anti-greenhouse effect caused by the haze particles, which reflect sunlight back into space, cooling the surface. The balance between these effects helps maintain Titan's stable climate over long periods. Another fascinating feature is the winds in Titan's atmosphere. Data from the Huygens probe during its descent showed that winds can reach speeds of several meters per second, and they change direction with altitude. These winds are responsible for shaping the vast dune fields seen in Titan's equatorial regions, similar to sand dunes on Earth, but made of organic particles. The atmosphere is also layered, with different temperatures and compositions at different heights. For instance, there is a stratosphere where temperatures increase with altitude due to absorption of solar radiation by the haze. Studying these layers helps scientists understand how energy is transferred and how the atmosphere circulates. The methane in the atmosphere is not infinite. It gets destroyed by solar radiation over time. So, for Titan to have maintained its methane abundance over billions of years, there must be a source replenishing it. This source could be geological activity, such as cryovolcanism, where water and ammonia mixed with methane erupt from the interior, or it could be from the slow release of methane stored in clathrate hydrates in the crust. Understanding this methane cycle is crucial because methane is the fuel for the entire atmospheric chemistry engine. If the methane were to run out, the haze would eventually dissipate, and the active surface processes would slow down. The unique conditions in Titan's atmosphere have led scientists to speculate about the possibility of life that is fundamentally different from life on Earth. While life as we know it requires water as a solvent, on Titan, life could potentially use liquid methane or ethane. Such life forms would have to metabolize different chemicals and operate at much lower temperatures. Although no evidence of life has been found, the presence of complex organics and liquid environments makes Titan a prime target in the search for habitable environments beyond Earth. The study of Titan's atmosphere is not just about understanding one moon. It has broader implications for planetary science. By examining how an atmosphere with a different composition and under different conditions behaves, we can improve our models of climate and atmospheric processes in general. This knowledge can be applied to exoplanets, many of which may have atmospheres rich in methane or other hydrocarbons. Titan serves as a nearby example of a world that challenges our Earth-centric views. Missions like Cassini-Huygens have provided a wealth of data, but there is still much to learn. Future missions, such as the Dragonfly drone, will directly sample the atmosphere and surface materials, giving us even more insight into the complex chemistry at work. As we continue to explore, Titan's atmosphere remains a key area of interest because it holds clues to some of the biggest questions in science: how life might arise, how planetary environments evolve, and what other strange and wonderful worlds might exist in the cosmos. The haze that once hid Titan's surface from view is now seen as a gateway to understanding the profound processes that shape not just moons, but the very building blocks of life itself. So, with this dense atmosphere driving complex chemistry, it naturally leads to one of Titan's most Earth-like features, a full-blown, active hydrological cycle. But here is the twist on Titan. Water is rock-solid ice, and the liquid that flows, evaporates, and rains is methane and ethane. This is not a subtle difference. It is a fundamental shift in how a world operates. Titan is the only place we know of, besides Earth, that has a persistent cycle of liquid moving between the surface and the atmosphere. Imagine standing on Titan and seeing methane clouds gathering in the orange sky, followed by a drizzle of liquid methane falling onto a landscape where rivers of it carve channels through water ice bedrock, eventually emptying into vast seas. The temperatures are brutally cold, around minus 179 degrees Celsius, which is precisely why this works. At those temperatures, water is frozen solid and behaves like rock, but methane and ethane can exist stably as liquids. So, the entire cycle is based on these hydrocarbons. Methane, specifically, is the workhorse. It evaporates from the surfaces of lakes and seas, rises into the atmosphere, and cools until it condenses into clouds. Then, when conditions are right, it falls back as rain. This methane rain is not a gentle mist. Observations suggest it can be heavy, feeding into watersheds and creating the intricate network of river valleys and deltas seen by the Cassini spacecraft. These are not dry, ancient features. They are evidence of ongoing, active processes. The liquids accumulate in topographical lows, forming lakes and seas, most of which are concentrated in the polar regions, especially the North Pole. The largest of these, the Kraken Mare, is a massive body of liquid hydrocarbons larger than the Caspian Sea on Earth. So you have a complete system: evaporation from the seas, cloud formation, precipitation over land, runoff into rivers, and flow back into the seas. It is a closed loop, albeit with different ingredients. The role of ethane is also crucial. While methane is more volatile and dominates the atmospheric cycle, ethane is often mixed in the liquids on the surface. Particularly in the larger seas, ethane is less likely to evaporate quickly, so it can persist in these large reservoirs over time. Through photochemical reactions in the atmosphere, some methane is converted into more complex hydrocarbons that eventually settle out, which might deplete the methane supply if it were not replenished. This is where the geological side comes in. There must be sources, perhaps from the interior via cryovolcanism or from subsurface reservoirs, that feed methane back into the system to keep the cycle going over geological timescales. The seasons on Titan play a huge role in driving this cycle. A year on Titan, which is one orbit around Saturn, takes about 29 Earth years. Each season lasts for roughly 7.5 Earth years, during the long summer in the northern hemisphere. For instance, increased solar energy leads to more evaporation from the northern lakes and seas. This results in more cloud cover and rainfall in those areas, potentially filling the basins. Conversely, during the southern summer, the south might see more activity, though the distribution of liquids seems asymmetric, with more large seas in the north. This seasonal variation means that the hydrological cycle is not constant. It pulses over decades, shaping the climate and surface features in slow motion. The landscape itself bears the scars and blessings of this alien cycle. The river channels on Titan show patterns similar to those on Earth, with meandering and braided streams, indicating that the laws of fluid dynamics apply even with liquid methane. The drainage basins and watersheds are organised, and the erosion patterns suggest that the methane rain can be intense enough to move sediment, which on Titan is likely grains of water ice or solid organic compounds. The lakeshores show evidence of changing levels, perhaps due to seasonal evaporation and precipitation, and some features even suggest the presence of waves driven by winds, though directly confirming wave activity has been challenging. The presence of these liquids also affects the local microclimate. For example, a large sea like Kraken mare might influence humidity and wind patterns in its vicinity, similar to how large bodies of water do on Earth. This entire system is a powerful analogue for understanding hydrological processes in general. By studying Titan, we can learn how a cycle functions with a different liquid, under different gravity, and in a different chemical environment. It tests our models and expands our knowledge of what is possible. For instance, the viscosity and density of liquid methane are different from water, which affects how it flows and erodes. Methane is less viscous than water, so it might flow more easily, but the lower gravity on Titan, which is about 1/7 of Earth's, changes how sediments are transported and how rivers meander. Scientists use computer models to simulate Titan's hydrology, inputting what we know about its atmosphere and surface, and then comparing the results to observations. This helps refine our understanding of fluvial and climatic processes everywhere. Moreover, this cycle is tied to the organic chemistry we discussed earlier. The methane in the atmosphere is broken down by sunlight, creating those complex organic molecules that form the haze. Some of these molecules dissolve in the methane rain or settle onto the surface, potentially accumulating in the lakes and seas. This means that Titan's hydrological cycle is not just moving a simple liquid, it is transporting a soup of organic compounds, possibly including precursors to life. The lakes themselves could be environments where further chemistry occurs, especially if there is any interaction with a subsurface water ocean. However, that is a topic for another time. The key point is that the cycle is integral to Titan's identity as a dynamic world. It also raises astrobiological questions. While the surface is far too cold for life as we know it, the constant cycling of liquids and organics could create niches where novel biochemistry might emerge, perhaps using methane as a solvent instead of water. Even if life is not present, studying this cycle helps us understand the distribution and evolution of complex molecules in the solar system. From an exploration standpoint, understanding the hydrology is crucial for planning future missions. A lander or a boat would need to account for the possibility of methane rain, changing shorelines, and the properties of the liquid itself. The Dragonfly mission, for example, will fly to different sites and might encounter areas shaped by this cycle, providing ground truth data. In a broader sense, Titan's methane cycle challenges our Earth-centric view of habitability and processes. It shows that active or complex systems can exist with completely different chemistry. As we discover more exoplanets, some of which might be Hycean worlds or have hydrocarbon atmospheres, Titan serves as a nearby example to guide our interpretations. The continuous interplay between the atmosphere, the liquids, and the surface on Titan is a reminder that worlds can be vibrant and changing in ways we are only beginning to comprehend. So, the next time you think of a river or a rainstorm, remember that on a distant moon, a similar dance is happening, but with ingredients that transform the familiar into the profoundly alien. This constant churn of methane and ethane through the atmosphere inevitably leads to where the liquid ultimately gathers. The stunning lakes and seas, with the most magnificent collections found at Titan's North Pole. This is where the hydrological cycle culminates, pooling into the largest bodies of liquid known to exist anywhere beyond Earth. The sheer scale is humbling. The Kraken mare, for instance, is a colossal sea that dwarfs even the Caspian Sea on our own planet. Right next to it lies the Ligeia Mare, another massive body of liquid, and together with numerous smaller lakes, they form a polar landscape dotted with dark, smooth expanses that sharply contrast with the brighter, solid terrain. These are not mere puddles, they are deep, permanent features, with depths that Cassini radar measurements suggest can exceed 300 metres in places. Imagine standing on a shoreline there, looking out over a sea so vast its opposite shore is beyond the horizon, all under a hazy orange sky. The liquid in these seas is not water. It is a frigid cocktail primarily composed of methane and ethane, kept in a liquid state by the intensely cold surface temperatures of around minus 179 degrees Celsius. Ethane, being less volatile, tends to be more abundant in these large, stable reservoirs, while methane is the more active component that evaporates and rains. The coastlines of these seas are remarkably complex and Earth-like, featuring intricate patterns of bays, peninsulas, and even islands. Some areas suggest the presence of what might be analogous to terrestrial salt flats or evaporative basins, where liquid has receded and left behind deposits of organic sediments. The topography around these seas indicates that they are contained in genuine topographical basins, meaning the liquid flows and collects according to gravity, just like on Earth. The dynamics within these liquids are a major area of scientific interest. For a long time, the surfaces of these seas appeared eerily smooth in radar data, leading to questions about whether they were truly stagnant. However, further analysis and occasional observations have hinted at the possibility of waves driven by winds sweeping across the dense atmosphere. Detecting waves directly has been challenging, but scientists have looked for subtle signs like changing surface roughness or ghostly reflections that might indicate surface movement. The presence of waves would confirm that there is an active exchange of energy between the atmosphere and the sea, a key component of any climate system. Currents are also theorized to exist within these seas, potentially driven by tidal forces from Saturn's immense gravity or by temperature differences, slowly circulating the liquid hydrocarbons and any suspended particles. The composition of the seas might not be uniform. Some areas could be richer in methane, while others have a higher ethane concentration, leading to layered structures or varying densities. Seasonal changes play a huge role here. During the long northern summer, which lasts about 7.5 Earth years, increased solar energy likely leads to more evaporation from these seas, feeding the clouds and precipitation that then fall back into the watersheds. There is even evidence of changing shorelines, suggesting that sea levels might fluctuate over these long seasonal cycles. Much like lakes on Earth can rise and fall, the discovery of these seas fundamentally altered our perception of Titan, transforming it from a mysterious hazy moon into a world with recognizable geographical features. They are the end point of the alien rivers and streams, the sinks where the liquid completes its cycle before evaporating back into the sky. For future exploration, these seas represent both an incredible opportunity and a significant challenge. Concepts for missions have included a submarine designed to dive into the Kraken Mare, analysing its composition and searching for signs of complex chemistry or even clues to habitability. Operating in such an environment is daunting. The extreme cold, the unknown corrosive properties of the liquid hydrocarbons, and the communication delays with Earth all present engineering hurdles. But the scientific payoff would be immense, offering a direct taste of an extraterrestrial sea. From an astrobiological perspective, these liquid bodies are fascinating. While the surface is far too cold for water-based life, the seas are a reservoir of organic molecules, constantly being supplied by the soot from the atmospheric haze raining down. This creates an environment where novel chemical reactions could occur, perhaps even leading to structures or processes we have not imagined. The interface between the liquid and the solid seabed might be particularly interesting, where interactions could mimic prebiotic conditions. Furthermore, the possibility of a subsurface water ocean beneath the icy crust raises the tantalizing idea that there might be some exchange of materials, though that remains speculative. Studying these seas also helps us understand the long-term evolution of Titan. The presence of such large, stable bodies of liquid indicates that the methane cycle has been active for a very long time, likely millions or billions of years. This stability is puzzling because sunlight continuously breaks down methane in the atmosphere, so there must be a substantial reservoir or an active source replenishing it, possibly from the interior through cryovolcanism or from clathrate compounds in the crust. The seas themselves act as a buffer in this system, storing vast quantities of hydrocarbons that can slowly feed back into the atmosphere. In a broader sense, Titan's North Polar Seas are a benchmark for planetary science. They show that processes we once thought unique to Earth can occur with completely different materials on another world. As we discover more exoplanets, some of which might be icy worlds or have hydrocarbon atmospheres, Titan serves as a crucial reference point. The lakes and seas of Titan are not just static features, they are active, dynamic components of a complex world, integral to its climate, its chemistry, and its enduring mystery. They represent a destination, a scientific frontier, and a powerful reminder of the surprising diversity of worlds in our cosmic neighbourhood. Understanding them is key to unravelling the full story of Titan, from its hidden interior to its hazy skies, and perhaps one day we will sail upon these alien waters, uncovering secrets that have been waiting in the cold and the dark for eons. Beyond the dark, liquid expanses of the northern seas, the solid ground of Titan unfolds into a breathtakingly diverse and alien geological mosaic, a landscape shaped by forces both familiar and utterly strange. If you were to walk away from the shoreline, you would soon encounter vast, relatively flat plains that dominate the mid-latitudes. These plains are likely covered in a thick layer of organic sediments, a tar-like sludge that has snowed down from the atmosphere over eons, accumulating into soft, undulating fields. This material, composed of complex hydrocarbons processed by sunlight in the upper haze, gives these regions a relatively dark and uniform appearance in radar images. The plains are not entirely featureless. They are punctuated by smaller hills and what might be the remnants of older geological features. But their overall expanse suggests a long history of deposition, where material has settled out of the atmosphere and been redistributed by weak fluid flows. Moving towards the equator, the scenery changes dramatically. Here, you find immense fields of dunes, stretching for hundreds of miles and rivaling the largest sand seas on Earth. These are not golden dunes of silicate sand. However, they are dark, linear ridges made of solid hydrocarbon grains, perhaps the size of sand or fine gravel. The particles are thought to be bits of tholins and other organic polymers that have coagulated in the atmosphere and fallen to the surface. The winds on Titan, though not extremely fast, are persistent and strong enough in the dense atmosphere to lift and transport these grains, piling them into vast dune fields that align with the dominant wind patterns. The dunes often form long, parallel chains separated by interdune areas, creating a striped pattern visible from orbit. Their presence in the equatorial regions is a direct result of the global wind circulation, which concentrates aeolian activity in this zone, much like on Earth. Interspersed throughout these plains and dunes are more rugged terrains, mountains and hills that rise above the surrounding flatlands. These are not mountains of rock as we know them. On Titan, the bedrock is water ice, which at these cryogenic temperatures is as hard and rigid as granite. These icy highlands can form significant ranges, with peaks and ridges that suggest a tectonic origin. The forces squeezing and fracturing Titan's icy crust likely from tidal interactions with Saturn or internal cooling and contraction, have pushed up blocks of ice to create these prominent features. Some mountains appear isolated, while others form longer chains, and their slopes are often carved by channels, indicating that liquid methane rainfall has eroded them over time. The presence of these mountains proves that Titan is not a geologically dead world. It has internal energy that drives surface change. Fluvial erosion is a major sculptor across all these terrains. The methane rainfall we discussed does not just feed the seas, it also carves the land. River channels, both large and small, snake across the plains, cut through the dunes, and dissect the mountainous regions. These channels show familiar patterns of meandering and braiding, indicating that the laws of fluid dynamics and sediment transport apply even with liquid methane. The rounded ice pebbles seen at the Huygens landing site are testament to this fluvial activity, tumbled and smoothed by flowing liquid. In some areas, the erosion has created valley networks and canyons, revealing layers of ice and organic material underneath. This ongoing erosion constantly redistributes surface materials, washing sediments from the highlands down into the low-lying plains and potentially into the seas. Another key process that might be reshaping the surface is cryovolcanism. This is the eruption of volatile substances like water, ammonia, DOT, or methane mixed with other compounds instead of molten rock on Titan. This would mean volcanoes spewing a cold, muddy slurry onto the surface. While definitive cryovolcanoes are hard to identify, several candidate features exist, such as domes with flow-like patterns emanating from them. If active, cryovolcanism would provide a crucial link between the interior and the surface, potentially replenishing the methane in the atmosphere and depositing freshwater ice onto the landscape. It could also create new landforms, like flows and cones, adding another layer of complexity to the geological map. The interaction of all these processes, aeolian, fluvial, tectonic, and possibly cryovolcanic, creates a surface that is constantly, albeit slowly, being remodeled. The wind erodes one area and builds dunes in another. The rain cuts new channels and deposits sediments elsewhere, and internal forces uplift new mountains while others are worn down. This dynamic activity means that Titan's surface age varies from place to place, with some areas being very young and geologically active, and others being ancient and heavily cratered, though impact craters are relatively rare due to the ongoing resurfacing. Studying this morphology is not just about cataloguing cool features. It is essential for deciphering Titan's entire history. The distribution of dunes tells us about wind patterns and the availability of sedimentary materials. The river channels reveal past and present climate conditions, including rainfall intensity and frequency. The mountains and tectonic features provide clues about the internal structure and the forces at work within Titan, such as the extent of tidal heating and the possibility of a subsurface ocean influencing the crust. The plains offer a record of atmospheric deposition, preserving a history of the complex organic chemistry happening overhead. By piecing together this geological puzzle, scientists can reconstruct how Titan has evolved over billions of years. They can understand how its climate has changed with the seasons and over longer astronomical cycles, how its interior has cooled and deformed, and how the unique combination of materials and processes has created this one-of-a-kind world. Furthermore, this understanding has implications beyond Titan. By studying how landscapes form with different materials, water ice as bedrock, hydrocarbons as sediment, and methane as the flowing liquid, we gain insights into planetary processes that are universal. This knowledge can be applied to other icy moons in our solar system, like Europa or Enceladus, and even to exoplanets that might have similar conditions. Titan's surface morphology is a direct window into its soul, revealing a world that is both eerily familiar and profoundly alien, a testament to the endless variety of geological expression in the cosmos, every plain, dune, and mountain tells a story, and we are only just beginning to learn how to read it. But all those diverse landscapes, the plains, dunes, and mountains, are not just shaped by physical forces, they are also the repositories for something even more profound, the complex organic chemistry that turns Titan into a giant natural laboratory for prebiotic science. This is where we see processes that might mirror what happened on Earth before life ever emerged, all taking place in a deep freeze. The action starts high up in the atmosphere, where sunlight, particularly harsh ultraviolet radiation from the sun, and energetic particles from Saturn's magnetosphere bombard the simple molecules there. This energy slams into the methane and nitrogen that make up most of the atmosphere, breaking their chemical bonds and creating a soup of highly reactive fragments. These fragments are like scattered puzzle pieces, and they immediately start colliding and reassembling into new, more complex molecules. This cascade of reactions produces a staggering variety of organic compounds. We are talking about things like benzene, a ring-shaped hydrocarbon, and hydrogen cyanide, a molecule that is toxic to us but is a crucial building block for more complex chemistry. In laboratory simulations that recreate Titan's atmospheric conditions, scientists have even seen the formation of amino acids, which are the fundamental components of proteins, and nucleobases, which are the key parts of DNA and RNA. This is not speculation. It is chemistry that we can observe and replicate, showing that the steps toward life's ingredients can occur in environments far different from Earth. These newly formed molecules do not stay as gases. They begin to stick together, coalescing into tiny particles that grow larger and larger. This is what forms the thick, orange haze that shrouds the entire moon, blocking our view of the surface. These haze particles are essentially soot made of complex organic polymers, and they eventually become heavy enough to sink through the atmosphere. They drift down in a continuous, slow-motion snowfall, blanketing the entire surface in a layer of organic gunk. Over millions and billions of years, this has accumulated into deep deposits, likely hundreds of meters thick in some places, covering the plains and dunes we discussed earlier. So, the very ground underfoot on Titan is made of this organic material, mixed with water ice. Now, this surface is incredibly cold, around minus 179 degrees Celsius, which slows down chemical reactions dramatically. But this is where another layer of Titan's complexity comes in, the subsurface ocean, deep beneath the icy crust. Evidence suggests there is a global ocean of liquid water, likely mixed with ammonia, which acts as an antifreeze. This hidden ocean could serve as a protected primordial soup, a stable environment where the organic molecules raining down from above might eventually be delivered. If there are cracks or vents connecting the surface to the interior, or if impacts melt through the ice, these complex organics could find their way into the liquid water. Suddenly, in this warmer, liquid water environment, the chemistry could become much more active. The molecules could dissolve and interact in ways that are impossible on the frozen surface, potentially forming even more complex structures. This combination of two liquid environments, methane and ethane on the surface and water underneath, makes Titan uniquely interesting. It is like having two separate laboratories for prebiotic chemistry, one in the deep freeze with hydrocarbon solvents, and one in the relative warmth with water as a solvent. This duality expands the possibilities for where and how life's building blocks can assemble. The study of this chemistry is not just about listing molecules, it is about understanding the pathways. How do simple molecules like methane and nitrogen evolve into something as complex as a nucleotide? What are the intermediate steps? On Earth, these processes happened in warm oceans billions of years ago and have been overwritten by biology. On Titan, they are happening now, in a state of pause, allowing us to observe a snapshot of chemical evolution. This makes Titan a natural time machine, giving us a window into our own planet's distant past. Furthermore, the constant input of energy from sunlight and particles drives the system forward, preventing it from reaching a stagnant equilibrium. The methane cycle we talked about earlier plays a role here, too, as it circulates materials and potentially exposes organics to different conditions. For instance, molecules that fall into a methane lake might undergo different reactions than those lying on a dry dune. The winds that shape the dunes also redistribute these organic particles, mixing them across the globe. So, the entire world is involved in this grand chemical experiment. Investigating this is central to answering one of humanity's biggest questions. What are the necessary steps for the origin of life? By studying Titan, we can test our theories about abiogenesis, the rise of life from non-living matter. We can see which molecules form readily and which require special conditions. This knowledge helps us define the boundaries of habitability in the universe. If Titan, a world so cold and so different from Earth, can produce the ingredients for life, then the number of potential habitats in the cosmos expands enormously. It challenges the idea that life requires Earth-like conditions and pushes us to think more broadly. Future missions, like Dragonfly, are designed specifically to probe this chemistry. Dragonfly will land on Titan and fly to multiple locations, sampling the surface material to analyze its chemical composition directly. It will look for those complex organic molecules and try to understand their distribution and structure. This is a huge step beyond remote sensing, as it will give us ground truth data on what this organic sludge is really made of. The results could tell us how far the chemistry has progressed and whether any of the steps toward life have been taken. Even if we do not find life, understanding the prebiotic chemistry on Titan provides a baseline for what is possible. It helps us interpret data from other icy moons and from exoplanets. When we look at telescopes and see signs of complex molecules in atmospheres of distant worlds, our experience with Titan gives us a framework for understanding what might be going on there. In essence, Titan's value lies in its ability to show us a different path that chemistry can take, one that is independent of the water-based, warm conditions we associate with life. It is a reminder that the universe is creative and that the building blocks of life might be a common outcome of planetary evolution, even in the coldest corners of a solar system. So, as we learn more about its landscapes and its seas, we must also appreciate the invisible chemical factory that is constantly at work, painting the moon orange and sprinkling its surface with the very stuff that could, under the right circumstances, lead to something new and alive. Beneath the frozen surface and the complex organic chemistry, hidden from view and from the harsh conditions above, lies perhaps the most tantalizing secret of Titan, a global ocean of liquid water. This is not a metaphor or a mere possibility. Data from the Cassini mission provides strong evidence for a vast subsurface layer, a hidden sea locked away in the dark. The discovery did not come from a direct image, of course, but from clever measurements of Titan's gravitational field and its physical deformations. As Titan orbits Saturn, it experiences intense gravitational tides from the giant planet. These forces squeeze and stretch the moon. By meticulously tracking how Titan's shape changes during its orbit, scientists could determine that its surface flexes much more than it would if the moon were entirely solid. This flexibility suggests a layer beneath the crust that is decoupled from the surface. Something slippery and global, a liquid ocean. Furthermore, precise measurements of Titan's gravity field, how it tugs on the Cassini spacecraft, reveal details about its internal mass distribution. which also points toward a dense, liquid layer sandwiched between the ice crust and a rocky core. This ocean is not a small lake. It is believed to be global, meaning it wraps around the entire moon, hidden under an icy shell that is probably dozens of kilometers thick. The depth of this ocean is still a subject of research, but it could be comparable to, or even deeper than the oceans on Earth, making it a truly massive body of water. But how can liquid water exist so far from the sun? The answer lies in a combination of factors. The primary source of heat is likely tidal heating. The gravitational pull from Saturn is not constant. It varies as Titan moves along its slightly elliptical orbit. This constant flexing and squeezing generates internal friction, which produces heat. This heat is sufficient to keep a layer of water liquid, especially when mixed with significant amounts of ammonia, which acts as a potent antifreeze, lowering the freezing point of the mixture dramatically. So, this is not pure fresh water. It is a briny, likely salty solution, rich in ammonia and other dissolved compounds. The existence of this ocean completely transforms our understanding of Titan's potential for habitability. It creates a second, entirely separate environment from the surface. While the surface is a laboratory for carbon-based chemistry with methane as a solvent, the subsurface ocean is a water-based environment much more familiar to us. The interaction between this liquid water and the rocky core at the centre of Titan is particularly exciting. On the ocean floor, there could be hydrothermal vents, similar to those found in Earth's deep oceans. These vents spew mineral-rich, heated water into the surrounding environment. On Earth, such vents are teeming with life, supporting entire ecosystems that thrive without any sunlight, relying instead on chemical energy. This process, known as chemosynthesis, could theoretically occur on Titan as well. The water-rock interactions could provide a continuous source of chemical energy and nutrients, creating potential oases for life. The ocean could therefore represent a protected habitat, shielded from the radiation and extreme cold of the surface, offering stability over geological timescales. This makes Titan a world with two potential arenas for life: the exotic, surface-based possibility in the hydrocarbon lakes, and the more familiar, water-based possibility in the deep ocean. The challenge, of course, is accessing this ocean. The ice shell above it is immensely thick, and punching through it with a probe would be a monumental engineering challenge, far beyond our current capabilities for a mission to the outer solar system. However, there might be natural connections between the surface and the ocean. Cryovolcanism, which we mentioned earlier, could be one such pathway. If cryovolcanoes on Titan are indeed erupting water-based slurries from the interior, they would be directly sampling this subsurface ocean and depositing its contents onto the surface. Future missions could land near such features and analyse the material, effectively tasting the hidden ocean without having to drill through the ice. Another connection could be through impacts that fracture the crust deeply, or even through slow exchange processes across the ice shell. The presence of this ocean also helps explain some of the mysteries of Titan's atmosphere. The methane in the atmosphere is continuously being destroyed by sunlight. To have persisted for billions of years, it must be replenished from a reservoir. This subsurface ocean, or the processes happening at its boundary with the rocky core, could be that source. Methane could be trapped in cage-like structures called clathrate hydrates within the ice, or could be released from the rock itself and slowly seep upward. The ocean itself might be involved in a complex geochemical cycle that we are only beginning to model. When we compare Titan to other icy moons, its subsurface ocean places it in a very elite category. Moons like Jupiter's Europa and Saturn's own Enceladus also have confirmed subsurface oceans. However, Titan's ocean is unique because of the incredibly active active and complex world happening above it. Europa has a young, cracked ice shell, but almost no atmosphere. Enceladus has geysers that vent ocean material into space, but its surface is mostly pure water ice. Titan has it all: a thick atmosphere, a complex surface geology with liquids and organics, and a hidden ocean. This makes it a comprehensive planetary system for studying the interplay between interior, surface, and atmosphere. Understanding Titan's ocean is therefore not just about Titan. It informs our search for life on all oceanic worlds. It teaches us about the conditions that can sustain liquid water over billions of years in the cold outer solar system. It shows that tidal heating is a powerful engine for maintaining habitability far from a star's warmth. As we look toward future missions, the characterization of this ocean is a top priority. Scientists want to know its exact depth and salinity, its composition, and whether it is in contact with the rocky core. They want to know if there are indeed hydrothermal systems on the seafloor. Answering these questions will require advanced radar sounders, seismometers to listen for moonquakes that reveal the interior structure, and maybe even a lander capable of detecting chemical signatures from the deep. The discovery of Titan's subsurface ocean turned a fascinating moon into a prime candidate in the search for life beyond Earth. It is a reminder that habitability is not always about surface conditions. Sometimes, the most promising environments are hidden from view, waiting in the dark, sustained by the internal heat of a world and the gravitational dance with its planet. This hidden sea is a cornerstone of Titan's story, a deep, dark, and mysterious layer that completes the picture of this world as one of the most complex and compelling places in our entire solar system. Now, while that hidden ocean churns in the darkness below, the evidence for its existence might not be entirely hidden. It could be leaking out, or even erupting, onto the surface through a process known as cryovolcanism. This is one of the most intriguing and yet to be confirmed aspects of Titan's geology. Imagine a volcano, but instead of spewing scorching molten rock, it erupts a cold, slushy mixture of water, ammonia, DOT, and other volatile compounds. That is the essence of cryovolcanism, or ice volcanism. On a world as cold as Titan, where water ice is as hard as bedrock, the presence of any kind of volcanic activity might seem counterintuitive, but it is a direct consequence of the internal heat we have been discussing. The tidal forces from Saturn, which help keep the subsurface ocean liquid, also provide the energy to potentially melt parts of the icy crust from below, creating reservoirs of this watery cryomagma. This material is less dense than the surrounding solid ice, so it seeks a path upward, eventually erupting onto the surface through fractures or vents. When this cryomagma reaches the surface, it does not flow like fiery lava on Earth. It immediately encounters the incredibly cold surface temperatures, around -179 degrees Celsius, causing it to freeze solid relatively quickly. However, if the eruption is substantial enough, it can form flows and deposits that reshape the local landscape before completely solidifying. The composition of this cryomagma is crucial. Ammonia plays a starring role here. When mixed with water, ammonia acts as a powerful anti-freeze, significantly lowering the melting point of the mixture. This means that the internal heat does not need to be as intense to create a liquid or slushy material that can migrate through the crust. A water-ammonia mixture could remain liquid at temperatures far below the freezing point of pure water, making cryovolcanism a much more feasible process on Titan. The resulting material erupting onto the surface would not be pure water ice. It would be a complex slurry, possibly containing various salts, organic compounds picked up from the interior, and dissolved gases. So, What would we actually see on the surface? Scientists analysing data from the Cassini mission have identified several candidate features that look suspiciously like cryovolcanic constructs. These include broad, dome-like structures that rise above the surrounding plains, often with flow-like features extending from their summits or flanks. Some of these domes appear to have fractured surfaces, hinting at the upward pressure of material from below. Other potential signs are lobate flows, smooth, tongue-shaped deposits that seem to have oozed across the terrain, covering older features like craters or river channels. These flows have a distinct appearance that sets them apart from the plains formed by atmospheric deposition or the channels carved by liquid methane. If these features are indeed cryovolcanic, they represent a powerful geological process that has helped to recycle Titan's surface. Cryovolcanism offers a mechanism to bring material from the deep interior, from that subsurface ocean or from the boundary with the rocky core all the way up to the surface. This is a big deal for several reasons. First, it could be a primary source for replenishing the methane in Titan's atmosphere. As we have discussed, methane in the atmosphere is continuously being destroyed by sunlight. For it to have persisted for billions of years, there must be a substantial reservoir or an active source. If cryovolcanoes are erupting, they could be releasing methane that was trapped in clathrate hydrates within the ice shell, or even methane that was produced through chemical reactions in the interior. This would solve the long-standing mystery of Titan's methane budget. Second, the ammonia in the cryomagma could be a key source of nitrogen for the atmosphere. Titan's atmosphere is overwhelmingly nitrogen, and while it was likely captured early in its history, maintaining it or processing it might involve internal sources. The eruption of ammonia, which can break down into nitrogen and hydrogen, could provide a steady trickle of new nitrogen, helping to maintain the atmospheric pressure over geological time. Furthermore, cryovolcanism provides a direct physical link between the hidden, potentially habitable subsurface ocean and the surface environment. If organic molecules are being synthesized in the ocean or at its boundaries, cryovolcanic eruptions could transport them to the surface, depositing them in a relatively pristine state. This would make certain locations on Titan incredibly interesting for future exploration, as a lander could potentially sample material from the interior without having to drill through kilometers of ice. It would be like getting a free sample delivered right to our doorstep. The detection of an active cryovolcanic plume, similar to the water vapour plumes on Enceladus, would be a monumental discovery. While nothing so dramatic has been definitively observed on Titan yet, scientists continue to scour the data for hints. Another tantalising possibility is the existence of lava lakes of water. These would be depressions on the surface filled not with methane, but with liquid water from a cryovolcanic vent, slowly freezing over time. Identifying such a feature would be challenging, as it might look similar to a methane lake in radar data, but careful analysis of its thermal properties and composition could reveal its true nature. Confirming cryovolcanism on Titan is difficult with the data we have. Many of the candidate features could also be explained by other processes, such as the intrusion of methane-saturated soils or the effects of tectonic stresses. The thick atmosphere and haze make high-resolution imaging a challenge, and without seismic data or in situ measurements, it is hard to be certain. This is where future missions come in. A mission like Dragonfly, which will hop across the surface, could potentially visit one of these candidate cryovolcanic sites. By analysing the chemical composition of the rocks and soils there, it could look for telltale signs of material that originated from deep within Titan, such as high concentrations of ammonia or specific isotopic ratios. If Dragonfly were to find a landscape composed primarily of water ice with ammonia hydrate, rather than the complex organic tholins that cover most of the surface, it would be strong evidence for a cryovolcanic origin. Understanding cryovolcanism is not just about Titan, It helps us understand geological activity on all icy worlds. Moons like Europa, Ganymede, Dot, and Enceladus also show signs of past or present cryovolcanism. By comparing these worlds, we can learn about the universal principles of how internal heat and material composition drive resurfacing processes in the outer solar system. On Titan, cryovolcanism represents a critical piece of the puzzle, connecting the deep interior to the atmosphere and the surface. It is a process that could have shaped the landscape, replenished the atmosphere, and perhaps even delivered the ingredients for life from the hidden ocean to the surface. While we await definitive proof, the very possibility adds another layer of dynamism to this already fascinating world, reminding us that even in the deep freeze, geological freezes can still burn. But all that internal activity, from cryovolcanism to the hidden ocean, ultimately interacts with and is influenced by what happens in the sky above. And that brings us to the grand, slow-motion drama of Titan's climate and seasons. This isn't a static, frozen world. It has a complex and dynamic weather system, but one that operates on a timescale almost incomprehensible to us. The entire engine is driven by two main factors: that incredibly dense atmosphere we've talked about, and Titan's orbit around Saturn, which itself takes a whopping 29 Earth years to complete one journey around the Sun. This means a single year on Titan lasts for 29 of our years, and this long orbital period dictates the rhythm of its seasons. Since Titan's rotation axis is tilted similar to Earth's, it experiences seasons, but each one is a marathon, not a sprint, lasting for approximately 7.5 Earth years. So, imagine a summer that lasts longer than a decade, or a winter that stretches across most of a human lifetime. This extended timeline means that climatic changes happen gradually, but can be incredibly dramatic over these long periods. During the long summer in the Northern Hemisphere, for instance, scientists using data from the Cassini mission observed a significant increase in the formation of thick, methane clouds over the North Polar region. This wasn't a fleeting afternoon shower. This was a seasonal shift that led to sustained rainfall, filling the vast lakes and seas like Kraken Mare and Ligeia Mare with fresh liquid methane. Conversely, during the southern summer, similar cloud activity and rainfall likely occur in the south, though the distribution of large liquid bodies is asymmetrical, with the north holding the majority of the big seas. This seasonal methane cycle is the heartbeat of Titan's climate, redistributing liquid across the globe and shaping the surface over eons. The driving force behind these seasonal changes is the sun's energy. As the Saturnian system travels around the sun, the hemisphere of Titan that is tilted towards the sun receives more sunlight and experiences summer, while the opposite hemisphere endures winter. But because the orbit is so long, the seasonal response is slow and sustained. The dense atmosphere plays a crucial role in storing and transporting this heat. Global wind patterns, somewhat similar to the Hadley cell circulation on Earth, help to redistribute heat from the warmer equatorial regions towards the colder poles. On Earth, the Hadley cell involves warm air rising at the equator, moving poleward at high altitude, cooling and sinking in the subtropics, and flowing back towards the equator near the surface. On Titan, a similar large-scale circulation exists, but it operates in a much thicker atmosphere and with different chemistry. These winds are responsible for moving not only heat, but also the tiny organic particles that make up the orange haze. This redistribution of haze can actually affect the temperature balance across the moon, as the haze particles absorb and scatter sunlight, influencing both greenhouse and anti-greenhouse effects. The winds themselves, while not hurricane force, are persistent and strong enough to shape the massive dune fields we see in the equatorial regions, aligning them with the dominant wind direction. The climate system is also influenced by the presence of the large liquid bodies, The seas and lakes act as reservoirs that can moderate local climate, much like oceans do on Earth. Evaporation from these seas provides the moisture for cloud formation and subsequent rainfall, creating a feedback loop that sustains the hydrological cycle. The changing seasons also affect the atmospheric pressure. Measurements suggest that Titan's atmospheric pressure might vary slightly with the seasons, as gases condense and evaporate from the poles. During winter in a hemisphere, the cold temperatures might cause more methane and ethane to condense and fall out of the atmosphere, potentially lowering the pressure, while summer warming leads to more evaporation and a higher pressure. This is still an area of active research, but it highlights the interconnectedness of all these systems. Another fascinating aspect is the potential for storm systems. While we haven't observed anything like a giant hurricane on Titan, the buildup of methane clouds in the summer polar region suggests organised weather patterns that could involve significant precipitation events. These rainstorms are likely what carve the river channels and feed the lakes, and they probably occur intermittently over the long seasonal period. The study of Titan's climate is not just an academic exercise. It provides an incredibly valuable counterpoint to our climate models on Earth. Here we have a world with a dense, nitrogen-based atmosphere, an active hydrological cycle, and a solid surface, just like Earth. But the working fluid is methane instead of water. The temperatures are cryogenic, and the seasonal cycles are 29 times longer. By running our climate models for Titan and comparing the predictions to what we actually observe, we can test the fundamental physics of these models. We can see if our understanding of fluid dynamics, heat transfer, and radiative balance holds up in a completely different environment. This helps us refine the models we use to predict Earth's climate future, because it strips away the complexities of biology and human activity, giving us a pure physical system to study. For example, the way haze particles interact with solar radiation on Titan can inform us about how aerosols might affect climate on Earth or other planets. The slow, deliberate pace of seasonal change on Titan also allows us to study long-term climate processes in a way that's difficult on Earth, where year-to-year variability can obscure longer trends. As we continue to observe Titan with telescopes like the James Webb Space Telescope, we can monitor these seasonal changes over time, watching how cloud patterns shift and how the surface might respond over decades. This long-term monitoring is crucial for understanding the full climate cycle. Furthermore, understanding Titan's climate is essential for planning future missions. A lander or a drone like Dragonfly would need to operate through Titan's day-night cycle and potentially through different seasonal conditions, which could affect everything from temperature to wind patterns to the possibility of methane rain. Knowing the climate helps engineers design systems that can survive and function in that environment. In a broader sense, Titan serves as a template for a class of planets we might discover around other stars, cold, with thick atmospheres, and possibly with hydrocarbon-based weather. By deciphering the climate of Titan, we learn how to interpret data from distant exoplanets. So, while the seasons on Titan are slow and long, the science they enable is rapidly evolving, offering us a unique laboratory to understand the principles of climate and weather on a truly global and alien scale. This slow dance of seasons, driven by a distant sun and mediated by a hazy atmosphere, completes the picture of Titan as a world that is not only geologically active, but also climatically vibrant. A place where the weather forecast is for a decade of drizzle followed by years of calm, all under an orange sky. All that detailed knowledge about Titan's climate, its seasons, and its surface features didn't just appear out of thin air. It was painstakingly gathered by one of the most ambitious robotic expeditions ever launched from Earth, the Cassini-Huygens mission. This incredible journey of discovery began back in 1997 when a powerful Titan IV rocket lifted off from Cape Canaveral, carrying the Cassini orbiter and the Huygens probe on a long voyage to the Saturnian system. The mission was a monumental collaboration between NASA, the European Space Agency, and the Italian Space Agency, representing a huge leap in international cooperation for planetary science. After a 7-year journey through the solar system, which included gravity assists from Venus, Earth, and Jupiter, the spacecraft finally arrived at Saturn in 2004. Cassini's primary mission was to study Saturn, its rings, and its moons, but Titan was always a central target, a world that had fascinated scientists for decades due to its impenetrable haze. The Cassini orbiter, equipped with a sophisticated suite of instruments including radar, infrared spectrometers, and cameras, began its work by entering orbit around Saturn. Over the next 13 years, Cassini performed more than 100 close flybys of Titan, each pass carefully planned to map different parts of the Moon, using its radar, which could pierce through the thick atmospheric haze. Cassini revealed the first clear views of Titan's surface, showing a stunningly diverse landscape. It discovered vast dunes of hydrocarbon sand stretching across the equator, broad plains that might be covered in organic sludge, and, most excitingly, lakes and seas of liquid methane and ethane, particularly clustered at the North Pole. The radar also hinted at possible cryovolcanoes and tectonic features, suggesting a geologically active world. Meanwhile, the Huygens probe, built by the European Space Agency, was patiently riding along with Cassini, waiting for its moment. On December 25, 2004, Huygens separated from the orbiter and began its own 3-week cruise toward Titan. On January 14, 2005, it entered Titan's atmosphere, beginning a historic descent. Protected by a heat shield, it slowed down from high speed and then deployed a series of parachutes to float gently down through the dense, orange sky. During its 2.5-hour descent, Huygens activated its instruments, sampling the atmosphere, measuring winds, and taking hundreds of pictures. It sent back data revealing a complex atmospheric structure with layers of haze and methane clouds. Then, it did something no human-made object had ever done before. It landed on the surface of a world in the outer solar system. Against all odds, Huygens survived the impact and continued to transmit from the surface for another 72 minutes, far exceeding its designed lifetime in that extreme environment. The data and images it sent were nothing short of revolutionary. The first pictures from the surface showed a plain littered with rounded ice pebbles, looking remarkably like a dry riverbed on Earth. The pebbles were smooth and worn, clear evidence of fluid erosion, likely from flowing methane. The landscape had a reddish-orange hue under the dim sunlight filtering through the haze. Instruments on board analysed the atmosphere and surface material, confirming the presence of methane and detecting complex organic molecules. A microphone even captured the sound of wind during the descent, providing a haunting, direct sensory experience of this alien world. The success of Huygens was a triumph of engineering and international partnership, and the data it collected alone would have been enough to mark the mission as a success. But Cassini's work was far from over. For years, the orbiter continued to study Titan, building up a detailed map of its surface and monitoring how it changed over time. It observed the shifting of clouds and the filling of lakes with the seasons, providing crucial data for understanding Titan's climate cycle. Its instruments detected evidence for a subsurface ocean of liquid water, adding another layer of mystery and potential habitability to Titan's story. The mission also studied Titan's interaction with Saturn's magnetosphere and its place within the broader system of moons. The Cassini-Huygens mission fundamentally transformed Titan from a fuzzy, mysterious orange ball into a complex, dynamic world with Earth-like processes. It showed us that Titan has weather, geology, and chemistry that, while alien in their details, follow physical principles we recognise. The sheer volume of data returned is so vast that scientists are still analysing it years after the mission ended in 2017 with Cassini's intentional plunge into Saturn's atmosphere. This deliberate end was chosen to prevent any possible contamination of Titan or Enceladus, moons that could potentially harbour life. The legacy of Cassini-Huygens is immense. It provided the foundational knowledge for almost everything we now know about Titan. It answered old questions and raised countless new ones, driving the planning for future missions. The images of Titan's surface from Huygens, the detailed radar maps from Cassini, and the atmospheric profiles are now textbook material, defining our current understanding of this fascinating moon. The mission demonstrated the incredible value of long-duration orbital exploration, allowing for the observation of seasonal changes and rare events. It also showcased the power of combining an orbiter with a lander, a strategy that might be used again elsewhere. For Titan, Cassini-Huygens was the key that unlocked the door, revealing a world that is both strangely familiar and profoundly alien. A place where rivers of methane flow into seas of ethane under a hazy orange sky. It set the stage for the next generation of explorers, like the Dragonfly mission, which will build directly on these discoveries. Without Cassini-Huygens, our view of Titan would still be shrouded in mystery. Because of it, we now see a world ripe for further exploration, a testament to human curiosity and our relentless drive to understand the cosmos. The mission remains a high point in space exploration, a reminder of what we can achieve when we work together across borders and dedicate ourselves to the peaceful exploration of our solar system. But beyond the orbital maps and the vast datasets, the Huygens probe gave us something even more profound, a sensory connection to this distant world, making the abstract tangible through sound and sight. The descent of Huygens through Titan's thick, orange atmosphere was not just a scientific measurement. It was humanity's first direct, multi-sensory experience on a world in the outer solar system. As the probe fell through the haze on January 14th, 2005, its instruments were not only collecting data, but also capturing the very sounds of this alien environment. Microphones on board recorded the roar of wind rushing past the heat shield during the initial high-speed entry, a haunting howl that was the first acoustic recording ever made from another moon. This wasn't a silent movie. It was a full-bodied experience, with the wind noise changing in pitch and intensity as the parachutes deployed and the probe slowed its descent, providing engineers with crucial data about atmospheric density and wind shear. Then, after the 2.5-hour descent, the probe touched down, and the audio sensors kept listening. The soundscape changed dramatically. The roaring winds were replaced by an overwhelming silence, a quiet so deep it was almost palpable, broken only by the faint mechanical hums and clicks of the probe's own instruments and the subtle sounds of its movements. This stark contrast between the violent descent and the eerie surface silence offered a powerful testimony to the profound stillness of Titan's surface, a place where the dense atmosphere muffles sound and where no natural noises, like birds or rustling leaves, exist. It was the sound of silence on an alien world, and it made Titan feel incredibly real and lonely. Simultaneously, the cameras on Huygens were busy capturing hundreds of images during the descent and after landing. The panoramic views revealed a landscape bathed in a dim, orange light filtering through the haze, showing a plain littered with countless rounded pebbles of water ice. These weren't jagged rocks. They were smooth and worn, clearly shaped by fluid erosion, likely from flowing methane in the distant or recent past. The scene looked remarkably like a riverbed on Earth, but the colouring was utterly alien, with hues of orange and red from the complex organic molecules coating everything. The images showed a relatively flat terrain, with hints of hills or raised areas in the distance, and the surface appeared to have a damp, almost wet consistency, though it was far too cold for liquid water. The analysis of the soil composition at the landing site, conducted by instruments that measured its physical properties, indicated a material with a consistency similar to wet sand or clay. But again, this was not water-based mud. It was a mixture of water, ice grains, and hydrocarbons, a sort of organic sludge that was rich in complex compounds like benzene and other molecules that had rained down from the atmosphere. This material, when a penetrometer on the probe poked it, behaved like a soft, damp solid, not a loose powder, suggesting that the surface might be cohesive and perhaps even hold moisture from liquid methane that had recently evaporated or soaked in. The combination of these sensory data, the sounds and the images, transcended the dry graphs and numbers that usually define scientific discovery. They transformed Titan from a data point into a place. For the first time, we could hear the wind of another world and see its landscape with our own eyes. Through the lens of the probe, it was no longer just a subject of study, it was a destination. The audio recordings, in particular, provided a unique window into the atmospheric dynamics. Scientists could analyse the wind sounds to determine wind speed and direction at different altitudes, refining models of Titan's atmospheric circulation. The silence on the surface confirmed the lack of significant seismic activity or weather noise at that moment, reinforcing the idea of a geologically quiet location. At least for the short time Huygens was operational, the images were equally transformative. They allowed geologists to study fluvial processes directly, confirming that erosion by liquid methane was a real and active force on Titan. The rounded pebbles suggested a history of transport and tumbling in liquid flows, and the overall topography indicated a landscape that had been shaped by both deposition and erosion over long periods. The fact that the surface was dark and relatively free of large craters also suggested that it was young and actively being resurfaced, either by aeolian processes from the wind-blown dunes or by the occasional methane rain shower. The sensory data also had a profound psychological impact on the public and the scientific community. Seeing those images and hearing those sounds made Titan accessible in a way that spectral data never could. It sparked the imagination and made the possibility of future exploration feel more urgent and personal. People could now picture themselves standing on that plain, under that orange sky, listening to the silence. This tangible connection is crucial for garnering support for missions and for inspiring the next generation of scientists and engineers. Furthermore, the success of Huygens' sensory instruments paved the way for including more advanced audio and visual equipment on future missions to other worlds, recognizing the immense value of experiential data. The probe's findings also raise new questions. The soil composition, for instance, suggests a surface that is chemically rich and potentially interesting for prebiotic chemistry. The organic sludge could be a repository for complex molecules that are the building blocks of life, and its physical properties would be important to know for designing future rovers or landers that might traverse this terrain. The images showed no immediate signs of life or liquid on the surface at that site, but they confirmed the environment where such chemistry could be ongoing. In essence, the Huygens descent and landing was a milestone in planetary exploration because it engaged multiple human senses, bridging the gap between cold data and warm experience. It reminded us that exploration is not just about measuring, it's about experiencing. The sound of silence on Titan is now a part of our collective human experience, a memory of a world we have touched with our technology and, in a way, with our senses. As we look forward to missions like Dragonfly, which will fly through Titan's atmosphere, we carry with us the legacy of Huygens, the knowledge that to truly understand a world, We must not only map it and analyse it, but also listen to its winds and gaze upon its landscapes, making the alien familiar one sound and one image at a time. But after hearing the wind and seeing those eroded pebbles, you might wonder what fluid could possibly shape a world so cold. The answer is methane, and it is the absolute keystone molecule that makes Titan the dynamic place it is, acting in almost the exact same way water does on our own planet. This simple compound, just one carbon atom bonded to 4 hydrogen atoms, is the workhorse of an entire world, driving everything from the global climate to the very geology of the surface. In Titan's atmosphere, methane exists primarily as a gas, and it plays a critical role in the Moon's greenhouse effect. This effect traps a small amount of solar heat, preventing the surface from becoming even colder than its already frigid -179 degrees Celsius. Without this atmospheric methane, Titan would be an even more intensely frozen wasteland. But the methane does not stay in the sky. It undergoes a continuous and active cycle. Energy from the sun, particularly ultraviolet radiation, breaks apart methane molecules in the upper atmosphere, initiating a complex chain of chemical reactions. This photochemistry leads to the creation of larger, more complex hydrocarbon molecules and nitriles, which eventually coalesce into the tiny particles that form the thick, orange haze obscuring the view. This haze is not just a passive shroud. It participates in the climate by absorbing and scattering sunlight, contributing to an anti-greenhouse effect that cools the surface, creating a delicate balance with the warming greenhouse effect. Meanwhile, lower in the atmosphere, methane gas condenses into clouds. These are not water vapour clouds. They are clouds of liquid methane droplets. When these clouds become saturated, they release precipitation in the form of methane rain. This rain is what carves the intricate network of river channels and valleys seen across Titan's landscape, eroding the water ice bedrock and transporting sediments. The liquid methane then flows across the surface, eventually pooling in topographical lows to form lakes and seas, predominantly found in the polar regions. These lakes and seas are not temporary puddles. They are vast, stable bodies of liquid, with the Kraken mare being the largest, acting as massive reservoirs in the global methane cycle. The methane then evaporates from the surfaces of these seas back into the atmosphere, completing the cycle and beginning the process all over again. This entire hydrological system, albeit with methane instead of water, is what makes Titan so uniquely Earth-like in its processes. However, there is a major puzzle surrounding Titan's methane. In the upper atmosphere, solar radiation is continuously destroying methane molecules, breaking them apart and converting them into other hydrocarbons. Over geological timescales, this photochemical destruction should have depleted all the methane in the atmosphere long ago. The fact that methane is still abundant means there must be a source replenishing it, a reservoir or a process that releases fresh methane to maintain the cycle. This is one of the central mysteries of Titan. Scientists have proposed several theories for this methane source. One compelling idea is cryovolcanism, where geological activity from Titan's interior releases methane trapped in the crust or from a subsurface reservoir. In this scenario, cryovolcanoes would erupt a cold slurry of water, ammonia, DOT, and methane, effectively venting the gas back into the atmosphere. Another possibility is that methane is stored in cage-like structures called clathrate hydrates within the icy crust, and it slowly seeps out over time due to thermal changes or geological shifts. There might also be a large subsurface ocean of liquid water that interacts with a rocky core, producing methane through chemical reactions that is then released upwards. Understanding this methane source is crucial because it sustains the entire active environment of Titan. Without this replenishment, the atmosphere would eventually clear, the rains would cease, the rivers would dry up, and the lakes would evaporate, leaving a much quieter and more dormant world. The methane cycle also has profound implications for the chemistry and potential habitability of Titan. The destruction of methane in the upper atmosphere produces a wealth of complex organic molecules that rain down on the surface. This constant organic snowfall accumulates into thick layers, covering the plains and dunes. These molecules are the building blocks of more complex chemistry, and in the presence of liquid methane or in the hypothesized subsurface water ocean, they could undergo further reactions. This has led to speculation about prebiotic chemistry, or even the possibility of life that uses methane as a solvent instead of water. Furthermore, methane is not alone in this cycle. It is often accompanied by ethane. In the large seas, ethane tends to be more abundant because it is less volatile and evaporates more slowly than methane. This means the seas are likely a mixture of both liquids, with ethane acting as a more stable long-term reservoir. The presence of these liquids also influences local weather patterns and climate, as evaporation rates vary between pure methane and ethane-rich mixtures. From an exploration standpoint, methane is both a target and a challenge. Future missions like Dragonfly will directly study the surface composition, including the distribution and form of methane and its related organics. If we ever establish a human presence on Titan, methane could be a valuable resource. It could potentially be used as a fuel for energy or as a raw material for manufacturing plastics and other materials, leveraging the abundant hydrocarbons available. The lakes of methane and ethane could essentially serve as natural gas stations for future explorers. However, operating in an environment dominated by methane presents difficulties, as the extreme cold and the chemical nature of the liquids could pose risks to equipment. Studying Titan's methane cycle also provides a critical analogy for understanding planetary climate systems. It shows how a hydrological cycle operates with a different fluid, under different gravity, and with a different atmospheric composition. This knowledge helps refine climate models that can be applied to exoplanets, many of which may have atmospheres rich in methane or other hydrocarbons. By observing Titan, we learn about the general principles of fluid dynamics, cloud formation, dot, and erosion processes in a completely alien setting. In essence, methane is the heartbeat of Titan. It drives the weather, shapes the landscape, fuels the chemistry, and presents one of the biggest scientific mysteries. Its continuous cycle from atmosphere to surface and back again is what makes Titan a living world in a geological sense, constantly changing and evolving. The search for its source is intertwined with the search for understanding Titan's interior and its history. Every raindrop of methane, every river channel, and every vast sea is a testament to the power of this simple molecule to shape a world. So, when you look at images of Titan's hazy orange globe, remember that it is methane that paints the picture, methane that carved the rivers, and methane that fills the lakes, making this distant moon a mirror to our own water-driven Earth, but in a cryogenic key. The persistence of this cycle over billions of years suggests a robust and active planetary system, and unravelling the secret of its methane source will bring us closer to understanding the full story of this fascinating world. With all that methane cycling through the atmosphere and shaping the landscape, it inevitably leads us to the most captivating question of all: could life actually exist on Titan? This isn't about finding little green men. It's about the possibility of life forms so fundamentally different from anything on Earth that they would challenge our very definition of biology. Titan is brutally cold, with surface temperatures hovering around minus 179 degrees Celsius, a place where water is frozen solid as rock. Yet, it's also incredibly rich in organic chemistry, with complex molecules constantly raining down from the haze. So the conditions are both forbidding and promising. Any life that might call Titan home would have to be truly exotic. potentially using liquid methane or ethane as its solvent instead of water. Think about that for a second. On Earth, all life we know relies on water to dissolve nutrients, facilitate chemical reactions, and transport materials within cells. On Titan, that liquid medium could be methane. This means the biochemistry would be entirely different. Such organisms might metabolize hydrocarbons, perhaps combining acetylene with hydrogen to release energy, or they might have cell membranes made from different compounds that remain flexible in the extreme cold, possibly using acrylonitrile-based structures. The two most promising environments for this kind of life are the lakes and seas of liquid hydrocarbons on the surface and the subsurface ocean of liquid water deep below the ice. Let's start with the surface. The lakes, like Kraken Mare, are vast bodies of methane and ethane. While incredibly cold, they are a soup of organic compounds. Life here would exist in a liquid environment, but one that is alien to us. It would face challenges like the low energy available from chemical reactions at such temperatures and the potential for cells to become too rigid. However, the constant supply of new organics from the atmosphere and the relative stability of these lakes over geological time could provide a niche. These hypothetical surface dwellers would not look like fish or algae. They might be microscopic, slow-growing, and adapted to a world where chemical processes happen at a much slower pace. Now, let's dive beneath the surface. Evidence strongly suggests a global ocean of liquid water, mixed with ammonia, exists tens of kilometers below the icy crust. This environment is much more familiar to us. It's dark, shielded from radiation, and potentially warm due to tidal heating from Saturn. On Earth, we find life thriving in similar extreme environments, like around hydrothermal vents on the ocean floor, where organisms use chemical energy instead of sunlight. If similar vents exist on the seafloor of Titan's subsurface ocean, they could provide the energy and nutrients for life. This life might be more similar to terrestrial microbes, using water as a solvent and relying on chemosynthesis. The exciting part is that these two potential habitats are not necessarily isolated. There could be exchange between them. Cryovolcanic activity might transport material from the subsurface ocean to the surface, or impacts could create temporary connections. So, how would we even know if life is there? We look for biosignatures, which are signs that can't be easily explained by non-biological processes. On Titan, one key biosignature could be an unexplained chemical imbalance in the atmosphere or on the surface. For example, if we detect a significant depletion of acetylene or hydrogen at the surface, it could indicate that something is consuming those compounds for metabolism. Similarly, if certain molecules are produced in abundances that don't match our models of atmospheric chemistry, that could be a red flag. Another biosignature might be the presence of specific complex molecules that are typically associated with biological processes, like certain isomers or enantiomers that favour one-handedness over another, which often happens in life. Detecting such subtle signs requires sophisticated instruments and careful analysis. This is where future missions come into play. The Dragonfly mission, set to arrive in the 20s, is a rotorcraft that will fly to multiple locations on Titan. It will carry instruments to analyse the composition of the surface material, looking for complex organics and potential biosignatures. It won't be looking for cells directly, but for the chemical footprints they might leave behind. Other proposed missions include submarines to explore the lakes or more advanced orbiters to monitor seasonal changes in atmospheric chemistry. The challenge is immense because we have to distinguish between the signatures of prebiotic chemistry, the natural, non-living formation of complex molecules, and actual biology. Titan is already a giant prebiotic laboratory, so finding interesting chemistry doesn't automatically mean life. We need to look for patterns that suggest metabolism, replication, or other hallmarks of living systems. This search forces us to broaden our perspective on habitability. For a long time, the habitable zone was defined as the region around a star where liquid water can exist on a planet's surface. Titan, far outside our sun's habitable zone, shows that habitability might be about having a liquid solvent and a source of energy, regardless of the temperature. If life can exist in Titan's methane lakes or in its hidden water ocean, then the number of potentially habitable worlds in the universe expands dramatically. It also raises profound questions about the origin of life. Is life a common outcome wherever you have complex chemistry and energy, or does it require very specific conditions? Studying Titan could help us answer that, even if we don't find life, understanding the limits of organic chemistry and prebiotic processes on Titan is incredibly valuable. It tells us what is possible without biology and helps us interpret data from other icy moons and exoplanets. The possibility of life on Titan is a powerful driver for exploration. It captures the imagination and pushes the boundaries of science. As we prepare for new missions, we are not just going to map another world, we are going to probe the very limits of life itself. The silence and cold of Titan might hide a secret that redefines our place in the cosmos, showing that life is not a rarity confined to Earth-like worlds, but a potential phenomenon that can arise in the most unexpected places, using the materials at hand to carve out an existence against all odds. So, while we wait for answers, Titan remains a beacon of mystery, a frozen world with a warm heart of scientific intrigue, challenging us to think bigger and look deeper. Given the profound questions about life that Titan presents, the natural next step is to gear up for a new wave of exploration. And the future looks incredibly exciting with a lineup of missions that sound like they are straight out of science fiction. The star of the show is undoubtedly NASA's Dragonfly mission, a bold and innovative project that is set to revolutionize how we study worlds with atmospheres. Imagine a large autonomous drone, essentially a sophisticated quadcopter, soaring through the thick orange haze of Titan, touching down in multiple locations to conduct detailed experiments. This is not a distant dream. Dragonfly is scheduled to launch in the mid-2020s and arrive at Titan in the mid-2030s, making it the first vehicle to fly its entire science payload to multiple spots on another world. The reason flying is so feasible on Titan is its dense atmosphere, which is about 50% thicker than Earth's, providing ample lift for rotorcraft. Dragonfly will be nuclear-powered, using a radioisotope thermoelectric generator to provide energy for its systems and to keep them warm in the extreme cold. Its primary goal is to investigate Titan's prebiotic chemistry and habitability. It will land initially in the equatorial Shangri-La dune fields, a region rich in organic sands, and then make flights of several kilometers to other sites, including the Selk impact crater, where evidence of past liquid water and organics might be preserved. On board, it will carry a suite of instruments including a mass spectrometer to identify complex organic molecules, a gamma-ray and neutron spectrometer to determine surface composition, and meteorological sensors to study Titan's weather. By hopping from place to place, Dragonfly will build an understanding of how complex chemistry evolves in different environments, directly addressing whether the building blocks of life can form and persist in such conditions. But Dragonfly is just the beginning, the vanguard of a much broader exploration campaign. Scientists and engineers are already dreaming up even more ambitious concepts for the post-Dragonfly era. One of the most captivating ideas is a submarine mission to explore Titan's seas. Picture a robotic submersible diving into the depths of Kraken Mare, the largest sea, navigating through liquid methane and ethane to map the seabed, analyze the composition of the liquid, and search for signs of chemical activity that could hint at life. Designing such a submarine is a monumental engineering challenge. The liquids are cryogenic, around -179 degrees Celsius, So all materials and electronics must be hardened against the cold to avoid becoming brittle. Power is another hurdle, with solar energy being extremely weak but far from the sun. The sub would likely need a nuclear power source like Dragonfly. Communication would be tricky too, with a one-way light time of over an hour to Earth, requiring the sub to operate autonomously for long periods. Despite these challenges, the science return would be unparalleled. It could measure the sea's depth, currents, and tides, sample the liquid for complex organics, and even look for thermal vents or other features on the seafloor that might support life. Another concept involves advanced orbiters. While Cassini provided a wealth of data, a next-generation orbiter could carry more powerful radar and infrared instruments to map the entire surface at higher resolution, monitor seasonal changes in detail, and study the interaction between the atmosphere and the surface over a full Titan year, which is 29 Earth years. Such an orbiter could also serve as a communication relay for surface assets like landers or submarines, ensuring a steady stream of data back to Earth. Speaking of landers, there are proposals for stationary platforms that could conduct long-term monitoring at a single site. These could be equipped with seismometers to listen for moonquakes and probe the interior structure, cameras to watch for weather events like methane rain or fog, and sophisticated laboratories to analyze surface samples in situ. Some concepts even include drills that could penetrate the icy crust to sample deeper layers or search for biosignatures. The overarching theme of all these future missions is to treat Titan as a system, understanding the connections between its interior ocean, its active surface, and its complex atmosphere. The scientific objectives are clear: to assess Titan's habitability definitively and to search for evidence of life, whether it is in the surface hydrocarbons or the subsurface water ocean. This requires a multifaceted approach because life on Titan could be very different from what we know. In the surface lakes, we might find life that uses liquid methane as a solvent, while in the subsurface ocean, life might be water-based, and similar to microbes on Earth, future missions will need to be equipped to detect biosignatures in both environments, which could include unexpected chemical imbalances, specific molecular patterns, or even structural fossils. The international space community is deeply invested in these plans, with agencies like the European Space Agency and others considering their own contributions. Collaboration will be key, as it was with Cassini-Huygens, to share costs and expertise. The timeline for these advanced concepts is still uncertain, as they require significant technological development and funding, but the scientific will is strong. Beyond the search for life, studying Titan helps us understand planetary processes in general, its Earth-like features, such as rivers, lakes, and dunes, but made of different materials, provide a valuable comparative planetology lab. Data from Titan can improve our models of climate, geology, and organic chemistry, which can be applied to exoplanets and other icy moons. The future of Titan exploration is a testament to human curiosity and our relentless drive to understand our place in the cosmos. Each mission builds on the legacy of Cassini-Huygens, pushing the boundaries of what is possible. As we develop new technologies, from advanced autonomy for robots to more efficient power systems, the vision of exploring Titan becomes more achievable. The coming decades promise to transform Titan from a distant, hazy moon into a familiar world, with its secrets slowly unveiled by our mechanical ambassadors. The journey is long, but the potential discoveries, perhaps even the first detection of life beyond Earth, make it a pursuit worth every effort. So, while we wait for Dragonfly to take flight and for new concepts to become reality, the anticipation grows, fueled by the knowledge that Titan holds clues to some of the biggest questions we can ask. Planning a mission to Titan is one thing, but actually building a spacecraft that can survive the journey and operate in that alien environment is a monumental test of human engineering. The challenges are unlike anything we face with missions to Mars or the Moon, and overcoming them requires innovation at every single step. After dreaming about all those incredible future missions, from Dragonfly to potential submarines, it is crucial to understand the sheer difficulty involved in making them a reality. Let us start with the most basic need: power. Titan is incredibly far from the Sun, about 10 times farther than Earth is, so sunlight there is extremely faint and diffuse. Using solar panels for energy is practically useless. They would have to be impossibly large to generate even a trickle of electricity. This is why missions to the outer solar system rely on a different power source altogether: radioisotope thermoelectric generators, or RTGs for short. These devices have no moving parts. They work by using the heat released from the natural decay of a radioactive isotope, like plutonium-238. This heat is then converted directly into electricity through thermocouples. It is a reliable and long-lasting source, but it comes with its own set of complications. The plutonium fuel is expensive, difficult to produce, and raises safety concerns during launch, as any accident could potentially release radioactive material. Furthermore, an RTG provides only a limited amount of power, which means every instrument and system on the spacecraft must be designed for extreme energy efficiency. You cannot run power-hungry equipment. Every watt is precious and must be budgeted carefully for the entire duration of the mission, which could last for years. Now, once you have figured out power, the next huge hurdle is actually getting the spacecraft onto the surface of Titan. This phase is known as entry, descent, and landing, or EDL, and it is a nail-biting sequence of events that has to work perfectly the first time. Titan has a very dense atmosphere, which is a double-edged sword. On one hand, that thick atmosphere is great for slowing down a spacecraft through atmospheric drag, and it is what allows for flight, as Dragonfly will demonstrate. On the other hand, it makes the descent incredibly complex. The Huygens probe provided a perfect example of this. It had to enter the atmosphere at a very precise angle. Too steep and it would burn up from the friction, too shallow, and it could skip off into space like a stone on a pond. After surviving the initial heat of entry, it deployed a series of parachutes in a carefully timed sequence to slow its fall from supersonic speeds to a gentle drift. The parachutes had to be designed to work in an atmosphere with a different density and composition than Earth's, and the entire sequence was automated because there is no way to control it from Earth in real time. For a larger or more complex lander, or for a flying vehicle like Dragonfly, the EDL process becomes even more complicated. You might need more sophisticated guidance systems to steer towards a safe landing site, and you have to account for unknown wind patterns and weather conditions. The surface itself is varied and poorly mapped, so the lander must be able to handle potentially rough terrain, whether it is a soft plain of organic goo, a hard water ice bedrock, or the shoreline of a methane lake. Then, after you have successfully landed, you face the challenge of communication. The distance between Earth and Titan is so vast that radio signals travelling at the speed of light take over an hour to make a one-way trip. That means if the spacecraft encounters a problem, it cannot wait for instructions from home. By the time engineers on Earth see the alert and send a response, at least 2 hours have passed, and the situation might have already become critical. This immense communication delay forces the spacecraft to have a high degree of autonomy. It must be able to monitor its own health, diagnose problems, and execute contingency plans on its own. For a mission like Dragonfly, which will fly to new locations, the drone must be able to navigate independently, assess landing sites for hazards, and decide for itself whether it is safe to touch down. This requires advanced software and robust computing systems that can operate without frequent human intervention. It is a level of self-sufficiency that we are only just beginning to develop for planetary exploration. But perhaps the most pervasive challenge is the extreme cold. Titan's surface temperature is around minus 179 degrees Celsius, which is colder than any place on Earth. At these cryogenic temperatures, ordinary materials and electronics simply fail. Metals can become brittle and shatter, plastics can crack, and lubricants can freeze solid. Every component, from the screws and wires to the circuit boards and sensors, must be specially selected or designed to withstand this deep freeze. Electronics are particularly vulnerable. Standard semiconductors stop working properly at such low temperatures, so they often need to be housed in a warm box called a warmed electronics enclosure, which is heated by waste heat from the RTG. This adds weight, complexity, and another point of potential failure. Alternatively, engineers are developing new types of electronics that can operate natively in the cold, but this technology is still in its infancy. The instruments themselves must be calibrated to function accurately in these conditions, as the properties of materials they are analysing, like the viscosity of liquid methane or the hardness of water ice, are completely different than what we are used to on Earth. Even simple movements, like deploying a robotic arm or rotating a camera, require mechanisms that will not jam or break when everything is frozen stiff. Furthermore, if a mission involves any kind of liquid sampling, like a submarine in Kraken Mare, the engineering challenges multiply. The submarine would need to be perfectly sealed to prevent the cryogenic liquids from leaking in and freezing internal components. Its propellers and control surfaces would have to operate in a fluid that is much denser and colder than water on Earth, and it would need sensors that can see through the potentially murky, organic-rich liquid. Power for a submarine would be even more constrained, and communication to the surface or an orbiter would be difficult through the liquid and the ice above. Every single aspect of the mission, from the initial design to the final operation, is a compromise and a trade-off between what is scientifically desirable and what is engineeringly possible. The mass of the spacecraft is always a limiting factor because launching more mass requires a bigger rocket and more fuel, which exponentially increases the cost. Therefore, engineers are constantly striving to make things smaller, lighter, and more power efficient. They have to test everything in simulated Titan environments on Earth, using vacuum chambers, cold chambers, and special liquids to mimic the conditions. Despite all these daunting obstacles, the history of space exploration shows that human ingenuity can prevail. The success of the Huygens probe is a shining example, and the lessons learned from it are directly informing the design of Dragonfly. Overcoming these challenges is not just about checking boxes for a mission, it is about pushing the boundaries of technology and expanding our capabilities as a species. Each solution developed for a Titan mission can have spin-off benefits for other fields, from materials science to autonomous robotics. The journey to Titan is a testament to our relentless curiosity and our ability to solve problems that seem insurmountable at first glance. It is a slow, meticulous, and often frustrating process, but the potential reward, unlocking the secrets of a world that could hold clues to the origin of life itself, makes every single engineering struggle worth the effort. So, the next time you hear about a planned mission to Titan, remember the incredible amount of work and innovation that goes into making it happen, from the nuclear battery that powers it to the autonomous brain that guides it, all built to survive in one of the most unforgiving environments we have ever dared to explore. After grappling with the immense engineering challenges of sending a mission to Titan, it is fascinating to step back and realise that all that effort allows us to do something profound. Compare this alien moon directly with our own planet, Earth. This is not just an academic exercise. It is a way to understand what is truly universal about how worlds work and what is unique to our own home. At first glance, Titan and Earth could not be more different. One is a moon orbiting a gas giant, shrouded in haze and drenched in methane, while the other is a rocky planet with blue oceans and a nitrogen-oxygen atmosphere. But when you look closer, the similarities in their processes are startling, even if the ingredients are radically swapped. Both Titan and Earth are incredibly active, dynamic worlds with systems that constantly reshape their surfaces. The most striking parallel is the presence of an active hydrological cycle. On Earth, we are familiar with the concept: water evaporates from the oceans, forms clouds, falls as rain, flows in rivers, and returns to the seas. Titan has the exact same cycle, but with methane as the working fluid. Instead of water, liquid, methane evaporates from the lakes and seas, forms methane clouds in the dense atmosphere, rains down, and carves river channels that flow back into the liquid bodies. This means both worlds have weather, precipitation, and flowing liquids that erode the landscape and create familiar features like valleys, deltas, and shorelines. The key difference, of course, is the temperature. On Earth, water is liquid within a comfortable range for life as we know it. On Titan, methane is liquid only because of the intense cold, around -179 degrees Celsius, where water is frozen solid and hard as rock. This swap in solvents leads to entirely different chemical environments, but the physical principles of evaporation, condensation, and erosion remain the same. Another major point of comparison is the atmosphere. Both Earth and Titan have atmospheres dominated by nitrogen. On Earth, nitrogen makes up about 78% of the air, with oxygen making up most of the rest. On Titan, the atmosphere is over 95% nitrogen, but it lacks significant free oxygen. Instead, it has methane and other hydrocarbons, and it is much denser at the surface level. The surface pressure on Titan is about 50% higher than on Earth, so it would feel like you are at the bottom of a swimming pool, but without the need for a pressurized suit. However, you would need serious thermal protection and a respirator because the air is not breathable and is incredibly cold. This thick atmosphere on Titan contributes to a greenhouse effect, similar to Earth's, but it is balanced by an anti-greenhouse effect from the haze particles that reflect sunlight. Both worlds have complex climate systems driven by their atmospheres, with global wind patterns redistributing heat and particles. On Earth, we have jet streams and trade winds. On Titan, there are similar large-scale circulation patterns that shape the weather over long seasonal cycles. The geology of these two worlds also offers a fascinating contrast. Earth's surface is dominated by silicate rocks, which form mountains, continents, and the ocean floor. Volcanism on Earth involves molten rock, and tectonics shift large plates over millions of years. Titan's geology is dominated by water ice. At those cryogenic temperatures, water ice is as hard and rigid as granite, so it forms the bedrock, the mountains, and the plains. Instead of silicate volcanoes, Titan might have cryovolcanoes that erupt a cold slurry of water, ammonia, DOT, and other volatiles. So, while the materials are different, the concepts of volcanism, tectonic forces, and mountain building appear to be universal processes that can occur with different substances. Erosion is another area where the similarities are eerie. Both worlds are sculpted by wind and liquid. On Earth, wind shapes deserts into sand dunes, and water carves canyons. On Titan, wind forms vast dune fields in the equatorial regions, but the sand is not silicate grains. It is likely grains of hydrocarbon particles that have coagulated from the atmospheric haze. These dunes can be hundreds of meters high and stretch for hundreds of kilometers, looking remarkably like the linear dunes in the Namib Desert on Earth. Meanwhile, the liquid methane on Titan erodes the water ice bedrock, creating river channels that look exactly like those on Earth, with meandering patterns and tributary networks. This tells us that the laws of fluid dynamics and sediment transport apply regardless of the liquid or the solid it is eroding. The presence of lakes and seas on both worlds completes the picture. Earth has vast oceans of water. Titan has large seas of methane and ethane, primarily at the poles. The shorelines of Titan's seas show features like bays, islands, and peninsulas, similar to coastal landscapes on Earth. However, the liquids behave differently. Methane is less viscous than water, and the lower gravity on Titan affects how waves and currents develop. Scientists are still studying whether Titan's seas have waves, but the potential for such dynamics highlights the universal nature of liquid bodies on planetary surfaces. When we compare the internal structure, both worlds have layered interiors, but with key differences. Earth has a molten iron core, a mantle of silicate rock, and a crust. Titan likely has a rocky core, surrounded by a layer of high-pressure ice, and then a subsurface ocean of liquid water, topped by an icy crust. This internal ocean on Titan, kept liquid by tidal heating from Saturn, is analogous to Earth's oceans in terms of being a liquid water environment, but it is completely isolated from the surface. On Earth, the oceans interact directly with the atmosphere and surface, driving climate and supporting life. On Titan, the subsurface ocean might be a separate habitat, potentially with its own chemistry. This comparison helps scientists isolate the fundamental principles of geophysics and climatology from those that are specific to Earth's chemistry. For example, DOT. By studying how a methane-based hydrological cycle operates, we can improve our climate models and apply them to exoplanets that might have similar conditions. It shows that processes like erosion, volcanism, and atmospheric circulation are not unique to Earth. They are outcomes of basic physics that can manifest on any world with the right conditions. This broadens our understanding of what makes a planet or moon active or dynamic. It is not about having Earth-like materials. It is about having energy sources and materials that can undergo phase changes and flow. Titan DOT, despite its cold and alien nature, is as geologically and meteorologically active as Earth, just in a different key. This realization has profound implications for the search for life. If life can exist on Titan, it would have to be based on a different biochemistry, perhaps using methane as a solvent. But the fact that Titan has liquid energy and complex organics means that the basic requirements for life might be more universal than we thought. Comparing Titan and Earth also helps us appreciate the uniqueness of our own planet. Earth's moderate temperatures, liquid water, and oxygen-rich atmosphere are perfect for life as we know it. But Titan shows that other configurations can support active, complex systems. As we explore more exoplanets, the Titan-Earth comparison serves as a guide for interpreting data from distant worlds. It teaches us to look for signs of processes rather than specific chemicals. For instance, if we see evidence of erosion, river valleys, or lakes on an exoplanet, we can infer active hydrology even if the liquid is not water. In the end, studying Titan is like looking at a distorted mirror of Earth. It shows us both how common and how rare our world might be. The similarities remind us of the universal laws of nature, while the differences highlight the incredible diversity of planetary environments. This comparative study is not just about listing features, it is about deepening our understanding of planetary science as a whole. By seeing how the same physical principles play out with different materials, we gain a richer, more nuanced view of the cosmos and our place within it. So, the next time you see a rainy day on Earth, remember that on a distant moon, a similar cycle is happening, but with liquid methane under an orange sky, and that connection makes the universe feel both vast and intimately familiar. But while comparing Titan to Earth shows us how different materials can create similar landscapes, it is crucial to understand the powerful, invisible hand that shapes Titan from the outside, the immense gravitational pull of its parent planet, Saturn. This relationship is not a gentle one. It is a constant, gravitational tug-of-war that fundamentally defines Titan's existence and its internal activity. Titan orbits relatively close to the giant gas planet, and this proximity subjects the Moon to intense tidal forces. Think of tides on Earth, where the Moon's gravity pulls on our oceans, causing them to bulge. Now, imagine that effect magnified tremendously, applied not just to a liquid surface, but to the entire solid body of a world. Saturn's gravity is so powerful that it literally stretches and squeezes Titan as it moves along its slightly elliptical orbit. This continuous flexing is not just a surface phenomenon. It generates heat deep within the Moon's interior through friction. As the rocky and icy materials inside Titan are deformed by this gravitational massage, they rub against each other, and that friction converts mechanical energy into thermal energy. This process, known as tidal heating, is a primary source of internal warmth for Titan, counteracting the intense cold of the outer solar system. One of the most obvious effects of this tidal relationship is something called tidal locking. Just like our Moon always shows the same face to Earth, Titan is tidally locked to Saturn. This means that Titan's rotation period on its axis is exactly equal to its orbital period around Saturn. As a result, one hemisphere of Titan permanently faces the gas giant, while the other always faces away. If you were standing on the Saturn-facing side, the planet would dominate the sky, a colossal, ringed spectacle that never moves from its fixed position. On the opposite side, you would never see Saturn at all. This locking is a direct consequence of the tidal forces over billions of years, which have gradually slowed down Titan's rotation until it reached this stable, synchronous state. However, the most significant impact of tidal heating is what it does for Titan's potential habitability. The internal heat generated by this flexing is likely a key factor in maintaining Titan's global subsurface ocean of liquid water. Without this energy source, the deep interior of Titan might have frozen solid long ago. The heat helps keep a layer of water liquid, probably mixed with ammonia acting as an antifreeze, between the icy crust and the rocky core. This hidden ocean is one of the most exciting aspects of Titan because it represents a potential habitat for life, shielded from the harsh surface conditions. The warmth from tidal heating could also be driving geological activity on the surface, specifically cryovolcanism. This is the eruption of water, ammonia, DOT, or methane slurries instead of molten rock. The internal heat might melt parts of the icy crust, creating reservoirs of this cryomagma that then push their way to the surface, forming features that look like volcanoes. If active, cryovolcanism would provide a crucial link between the interior ocean and the surface, potentially recycling chemicals and replenishing the methane in the atmosphere that is continuously being destroyed by sunlight. The tidal forces do not act in isolation. Titan's orbit and internal dynamics are also influenced by its gravitational interactions with Saturn's other moons. This is a complex orbital dance. Moons like Hyperion, Iapetus, Dot, and especially the inner moons, exert their own small but cumulative gravitational tugs on Titan. These interactions can cause slight perturbations in Titan's orbit, making it more elliptical or influencing its orientation. This, in turn, can affect the intensity of the tidal heating. If the orbit becomes more elliptical, the variation in gravitational pull from Saturn as Titan moves closer and farther away would be greater, leading to more intense flexing and more internal heating. This interplay between multiple moons helps maintain the dynamic environment of the Saturnian system and ensures that the tidal heating is not a constant but a variable process over long timescales. Studying this system provides a classic example of how a giant planet can sculpt the evolution and potential habitability of its moons. It is a demonstration of celestial mechanics in action, showing how gravity can provide the energy needed to sustain liquid water and geological activity far from the sun's warmth. This concept extends beyond our solar system, as we discover exoplanets. Many of them are gas giants orbiting close to their stars, and they likely have moons of their own. Understanding how tidal forces work on Titan helps us model the potential for similar subsurface oceans on exomoons, expanding the search for habitable environments in the universe. The tidal relationship also has implications for Titan's surface features. The stress from the tidal forces could contribute to tectonic activity, cracking the icy crust and creating mountain ranges or faults. These fractures might serve as conduits for cryovolcanic material or as channels for liquids moving between the surface and the interior. Furthermore, the tidal locking means that the distribution of solar energy on the surface is fixed relative to Saturn, which could influence climate patterns, though the thick atmosphere probably redistributes heat fairly effectively. The constant gravitational pressure from Saturn also affects Titan's shape. Although it appears spherical, it is likely slightly elongated, bulging a bit along the axis pointing towards Saturn due to the tidal pull. This deformation is small but measurable and provides clues about the Moon's internal structure, such as the rigidity of its ice shell and the viscosity of its interior. In essence, Titan is not an independent world. It is a product of its environment, intimately tied to Saturn. The planet's gravity provides the energy that keeps Titan geologically alive and potentially habitable in its deep ocean. This external driving force is what allows Titan to have such a complex and Earth-like system of liquids and weather on its surface, even though the ingredients are completely different. Without Saturn's tidal influence, Titan might be a frozen, dormant ice ball. With it, it is a dynamic world with a hidden, liquid heart, a testament to the power of gravitational relationships in shaping the nature of worlds. As we continue to explore Titan with future missions, understanding this tidal connection will be key to interpreting the data we collect about its interior, its geology, and its potential for life. It reminds us that in the cosmos, no world is an island. Each exists within a web of gravitational interactions that define its fate and its character. But to fully grasp how Titan became the world it is today, shaped so profoundly by Saturn's gravity, we need to rewind the clock billions of years and look at its very origins. How did this complex moon form in the first place? And what can its birth tell us about other worlds? The story of Titan's formation is an active area of research, but the prevailing theory paints a fascinating picture of cosmic construction within a swirling disk of material around a young Saturn. In the early solar system, after the sun ignited, the planets were forming from the vast protoplanetary disk of gas and dust. Saturn itself coalesced from this material, and as it grew, it was surrounded by its own spinning disk of gas and dust, known as a circumplanetary disk. Think of it as a miniature version of the solar system's protoplanetary disk, but centered on Saturn instead of the Sun. It was within this dynamic, swirling environment that Titan and Saturn's other moons began to take shape. The process likely started with tiny particles of ice and rock within the disk. These particles collided and stuck together through electrostatic forces, gradually building up into larger bodies called planetesimals. Over time, through a process of accretion, these planetesimals collided and merged, with the largest ones sweeping up more material due to their stronger gravity. Titan grew by accreting these planetesimals, which were rich in water ice and rocky material, in a process very similar to how the planets themselves formed around the Sun. This explains Titan's substantial size. It had a large feeding zone within Saturn's disk and managed to become the dominant moon. The composition of these building blocks is key to understanding Titan today. The planetesimals were probably similar to comets or icy asteroids, containing ices like water, ammonia, DOT, and methane clathrates. As Titan grew, the energy from these collisions and from the decay of radioactive elements in its interior would have heated it up. This early heat might have caused differentiation, where the denser rocky material sank to form a core, while the lighter ices rose to form a mantle and crust. This internal structure is crucial for supporting the subsurface ocean we believe exists today. Now, one of the biggest puzzles is Titan's atmosphere. How did a moon acquire such a thick DOT, nitrogen-rich envelope? There are two leading ideas. One possibility is that Titan captured its atmosphere directly from the gases in Saturn's circumplanetary disk. As Titan formed, its gravity could have drawn in nitrogen and methane from the surrounding nebula, trapping them and creating an initial primitive atmosphere. The other, perhaps more likely, scenario involves outgassing from the interior. The heat from accretion and radioactive decay could have vaporized volatile compounds trapped within the icy planetesimals that built Titan. Ammonia, DOT, in particular, is a key player here. If Titan's building blocks contained ammonia ice, internal heating could have broken it down into nitrogen and hydrogen. The lightweight hydrogen would have escaped into space, while the heavier nitrogen was retained, slowly building up the dense atmosphere we see today. Methane could have been released in a similar way from the breakdown of methane clathrates stored in the ice. This outgassing process might have continued over geological time, helping to replenish the atmosphere against losses to space. The formation of Titan was not a calm process. It was likely violent and chaotic, with many large impacts occurring in the crowded disk. A giant impact might even explain some of Titan's odd characteristics, such as its orbital inclination or its specific internal structure. The timing of Titan's formation is also important. It probably formed within the first few million years of the solar system's history, around the same time as Saturn itself was finishing its growth. As the circumplanetary disk cooled and dissipated, the major era of moon formation came to an end. Titan's location within the disk would have determined its initial composition and available materials. Being farther out in the solar system, where temperatures are colder, meant that volatile ices like methane and ammonia could condense and be incorporated into the forming moon, which is why Titan is so ice-rich compared to, say, the moon of Earth. Understanding Titan's formation helps us make sense of its unique properties today. Its large size and complex interior are direct results of its accretion history. Its atmosphere is a legacy of the materials it formed from and the internal processes that followed. This knowledge also helps us contextualize Titan within the family of Saturn's moons. Why is Titan so different from, say, Enceladus or Iapetus? The answer lies in their different formation locations and histories within the circumplanetary disk. Some moons might have formed closer to Saturn, where temperatures were hotter, preventing the incorporation of many volatiles, while Titan formed in a more favourable region. Furthermore, the study of Titan's formation has implications far beyond our solar system. As we discover more exoplanets, many of them gas giants, we can infer that they likely have their own systems of moons formed in circumplanetary disks. By understanding how Titan formed, we can predict what kinds of moons might exist around these distant worlds and whether they could be habitable. If moons like Titan are common, then the number of worlds with thick atmospheres and liquid on their surfaces might be much higher than we thought, even if that liquid is methane instead of water. The formation process also set the stage for Titan's long-term evolution. The initial heat from accretion and the ongoing tidal heating from Saturn have kept Titan geologically active. driving processes like cryovolcanism, and maintaining the subsurface ocean. The materials delivered during formation provided the raw ingredients for the complex organic chemistry that now defines the Moon. In a way, Titan's formation was the first step in creating a prebiotic laboratory that has been running for billions of years. Scientists use sophisticated computer models to simulate these formation scenarios, inputting what we know about the early solar system and the composition of comets. They test different ideas about the disk's temperature, density, dot, and lifetime to see which conditions best reproduce Titan as we observe it today. Missions like Cassini provided data that constrain these models, such as precise measurements of Titan's gravity field and composition. Future missions might bring back samples that could directly tell us about Titan's building blocks, though that is a long-term goal. In summary, Titan did not simply appear. It was constructed piece by piece in the disk around a young Saturn, from countless icy planetesimals. This origin story explains its size, its structure, and the seeds of its atmosphere. It connects Titan to the broader narrative of planetary formation, showing that the processes that built the planets also operate on smaller scales around giant worlds. By studying Titan's birth, we learn not only about this one moon, but about the fundamental ways that worlds come into being, both in our cosmic neighbourhood and across the galaxy. This perspective makes Titan more than just a destination. It is a time capsule, preserving the conditions of the early solar system and offering clues to the origins of all planetary systems. From its violent origins in the disk of Saturn to its present-day complexity, Titan has always held a unique power over the human imagination, transcending its role as a mere scientific target to become a canvas for our dreams of adventure and a potential future home. Long before we had detailed maps from Cassini, Titan was a fixture in science fiction, a world where writers could envision alien landscapes and possibilities far beyond our own solar system. Authors like Arthur C. Clarke, Dot, in his novel Imperial Earth, and Kim Stanley Robinson, in his Mars trilogy, used Titan as a backdrop for stories of exploration and human expansion, painting it as a distant, mysterious outpost on the frontier of known space. Its impenetrable haze was a perfect screen onto which we could project our fantasies of what might lie beneath, whether it was strange life forms, ancient ruins, or simply a beautiful and deadly wilderness. The film Ad Astra brought this vision to a modern audience, depicting a journey to the outer solar system where Titan served as a dramatic setting for a lunar base and a pivotal moment in the narrative. This cultural presence is important because it fuels public interest and inspires the next generation of scientists and engineers who will turn these fictions into reality. But beyond its role as a storytelling device, Titan is now being seriously considered as a potential site for a future human colony, a concept that moves it from the realm of pure fantasy into the domain of strategic planning. The reasons for this are surprisingly practical, rooted in the very resources that make Titan so scientifically interesting. First and foremost, Titan offers a crucial form of protection that almost no other world in the outer solar system can provide: a dense atmosphere. That thick blanket of nitrogen and methane provides a substantial shield against cosmic radiation and solar flares, which are major health risks for astronauts on airless worlds like the Moon or Mars. On Titan, you would not need to live buried underground for radiation protection. You could theoretically walk on the surface with just a warm suit and a respirator, enjoying the view of Saturn in the sky, without fear of a lethal radiation dose. Secondly, Titan is rich in resources. The rivers and lakes are not filled with water, but with liquid methane and ethane. These hydrocarbons can be seen as natural deposits of fuel. With the right technology, they could be processed into energy for power generation or used as rocket propellant. This means a colony on Titan could potentially produce its own fuel for surface vehicles, for heating, and for return journeys to Earth. making it far more self-sufficient than a base that has to import every ounce of propellant. Furthermore, the abundant carbon and nitrogen in the atmosphere and on the surface could be used to manufacture plastics, fertilizers, and other essential materials for a sustained human presence. The very organic chemistry that makes Titan a prebiotic laboratory could also make it an industrial park for a future settlement. Water, while frozen solid on the surface, is also abundant in the form of water ice, which dominates the geology. This ice could be mined and melted for drinking water, split into oxygen for breathing and hydrogen for fuel, or used as a raw material for construction. Building structures from sintered ice blocks is a real concept for outer planet colonization, providing robust and readily available building materials. The challenges, of course, are immense and cannot be overstated. The cold is almost unimaginable, a persistent minus 179 degrees Celsius that would threaten any mechanical system and require constant energy for heating habitats. The sunlight is incredibly faint, making solar power virtually useless and necessitating robust nuclear power sources like the RTGs used on spacecraft. The psychological toll of living in a dim, orange-hazed world, with Saturn looming large in the sky and communication delays to Earth lasting over an hour, would be profound, requiring careful selection and support for any colonists. The logistics of getting there and supplying a colony are staggering, involving years of travel time and immense cost. Yet, the vision persists because the potential payoff is so high. A colony on Titan would represent humanity's first permanent foothold in the outer solar system, a stepping stone to even farther destinations. It would be a hub for scientific research, allowing for the continuous, in-depth study of Titan's environment, its potential for life, and the Saturnian system as a whole. Imagine geologists conducting fieldwork on the shores of Kraken Mare, or biologists analysing samples from the subsurface ocean delivered by cryovolcanoes, all supported by a permanent human presence. This vision of Titan as a future colony is more than just a technical blueprint. It is a powerful symbol. It represents the enduring human drive to explore, to push into new frontiers, and to establish a presence beyond our cradle of Earth. It combines the pragmatic need for resources and safety with the timeless romanticism of exploration that has always driven us to look at the stars. Scientists, engineers, and dreamers are all united by this possibility, using it to drive innovation in everything from closed-loop life support systems to autonomous construction in extreme environments. The journey from seeing Titan as a point of light in a telescope, to a mapped world revealed by Cassini, to a future home for humanity, is a testament to how our understanding evolves. It shows that exploration is not just about collecting data, it is about expanding the realm of human possibility. Titan, with its protective atmosphere and abundant resources, offers a unique and compelling case for being that next great step. So, while the challenges are real and the timeline is likely centuries long, the very act of seriously considering it changes our perspective. It transforms Titan from a distant object of study into a potential chapter in the human story, a place where our descendants might one day live, work, and look back at Earth as a tiny blue dot in the sky, a reminder of where we came from and how far we have journeyed. This fusion of science and imagination ensures that Titan will remain a focal point of our ambition, a world that challenges us not only to understand it, but to one day call it home.